There are objects in history that transcend their physical form. Blades that became legends, whispered about in markets and palaces, their capabilities stretching beyond what seemed possible. Among all the treasures of the ancient world, few captured the imagination quite like Damascus Steel. And tonight, as you rest, we'll explore the mystery of these remarkable blades, their secrets, their science, and the legends that still echo through time. Picture, if you will, a master swordsmith in medieval Damascus, holding up a blade to catch the light. The surface ripples with patterns like water frozen in metal, dark bands flowing across bright steel in mesmerizing waves. But beauty was only the beginning of the story. What made these blades truly legendary wasn't just how they looked, it was what they could do. The tales that spread across trade routes spoke of impossible feats. Merchants and warriors carried stories from the Middle East to the courts of Europe, each account more remarkable than the last. And among these stories, one test captured the imagination above all others: the test of the silk scarf. Imagine a piece of silk, delicate and weightless, tossed into the air. As it drifts downward, floating on invisible currents of air, a Damascus blade is held perfectly still. The silk lands on the edge and parts. Just like that. No sawing motion, no force. The scarf's own weight is enough. The blade slices through the gossamer fabric as it falls through the air, the two halves fluttering separately to the ground. This wasn't merely sharp. This was something beyond the ordinary understanding of an edge. European blades of the time were formidable weapons, certainly capable tools of war and craft. But they couldn't do this. A silk scarf would drape over their edges, conforming to the steel, perhaps eventually sliding down, but not parting, not severing mid-air from its own negligible weight. The Damascus blade achieved something that seemed to violate the rules of metallurgy as medieval craftsmen understood them. To cut requires force applied against resistance. But silk falling through air provides almost no resistance, and gravity provides only the smallest force. Yet the Damascus edge was so keen, so perfectly formed at a microscopic level, that this whisper of force was enough. Think about what this means for a moment. Consider the precision required. The edge of a blade, examined closely, is never truly smooth. It's a series of peaks and valleys at the microscopic level, like a mountain range viewed from high above. For most blades, these irregularities are large enough that soft materials simply press into the valleys rather than parting. But Damascus steel achieved something finer. An edge so refined that even silk couldn't find purchase. It simply separated. This test became legendary because it was demonstrable. It wasn't a story of a battle no one witnessed, or a feat no one could verify. A merchant could see it with his own eyes. A silk scarf was expensive, yes, but not impossibly rare. The test could be repeated, and apparently, it was repeated again and again across centuries, becoming one of the defining proofs of a true Damascus blade. But the silk scarf test was just the beginning of the legend. There were other stories, harder to believe, yet told so consistently that they demanded consideration. Stories of Damascus blades striking stone and emerging unscathed. Not just tapping against rock, but actually shattering it. While the blade itself remained whole, unmarred, still perfectly sharp. In the medieval world, this seemed impossible. Rock is harder than steel. This was understood. Strike an ordinary blade against stone with force, and the steel would chip, or the edge would roll over, or in the worst cases, the blade would crack entirely. Metal might be strong, but stone was harder. This was simply how the world worked. Yet the reports persisted. Damascus blades, wielded with full force against rock, would shatter the stone. The rock would give way, and the blade would remain perfect. How could this be? The answer, though it wouldn't be fully understood for centuries, lay in the internal structure of the steel itself. Damascus blades weren't simply hard or simply tough. They were both simultaneously, in ways that seemed contradictory. But we're getting ahead of ourselves. For now, simply hold on to the image. A blade striking stone, the stone shattering, and the blade emerging unmarked. A feat that defied expectation. And if a blade could remain sharp through impacts that would destroy ordinary steel, Imagine how long it could hold an edge through normal use. This was perhaps the most practically valuable property of Damascus steel: its edge retention. Sharpness that lasted not just days or weeks, but months. Even years, according to some accounts. While European knights had to regularly sharpen their weapons, carefully maintaining the edge through repeated honing, a Damascus blade seemed to resist dulling through some internal magic. Sharpness, you see, is always temporary. Every cut, every impact, every moment of use slowly degrades the finest edge. Microscopic chips form. The metal at the very edge compresses slightly. Oxidation forms tiny imperfections. Bit by bit, the keen edge becomes merely sharp, then merely adequate, then dull. But Damascus steel resisted this degradation far longer than it seemingly should. A blade that could be used day after day, week after week, and still pass the silk scarf test. Still slice through rope and leather, and wood with barely any resistance. This wasn't just convenient. In an era where a warrior's life might depend on his blade, and where a craftsman's livelihood depended on his tools, this was invaluable. The edge seemed almost alive, persistent, refusing to surrender its keenness to the ordinary forces of wear and time. And yet, here's where Damascus steel became truly mysterious. Because everything I've just described suggests a metal of extraordinary hardness. Hard steel holds an edge longer. Hard steel can shatter rock. The harder the steel, the better it resists wear. But hardness comes with a terrible price. Hard steel is brittle. Strike a very hard blade against something solid, and it doesn't just dull, it shatters. The blade breaks, sometimes explosively, sometimes with a clean crack that leaves you holding a useless handle attached to half a sword. Damascus steel shouldn't have been able to do what it did. It combined properties that were supposed to be mutually exclusive. It was hard enough to shatter rock, and flexible enough to bend without breaking. These aren't supposed to coexist. In metallurgy, there's almost always a trade-off. You can have hard steel or tough steel, but not both. You can have flexibility or rigidity, but not both. You can have an edge that holds forever or a blade that absorbs impacts, but not both. Damascus steel seemed to laugh at these limitations. A Damascus blade could be flexed, bent into a curve, and spring back to true without taking a permanent set. The high carbon content that made it hard should have made this impossible. High carbon steel is crystalline, rigid, wanting to maintain its structure. Bend it too far and it doesn't flex, it fractures. But Damascus blades flexed. Warriors could test them by bending the blade significantly and watching it return to perfect straightness. A party trick, perhaps, but also a deeply practical assurance. In combat, impacts come from unexpected angles. A weapon might be struck from the side, or twisted, or subjected to forces its maker never imagined. A brittle blade breaks. A flexible blade survives. Damascus steel survived. Word of these properties spread, as word always does. And as the centuries passed, these blades developed a reputation that extended far beyond the Middle East, where they were forged. In Europe, a Damascus blade was a treasure beyond price. Knights and nobles who acquired them treated them as heirlooms, weapons to be passed from father to son, their value only increasing with time. In battle, a warrior bearing a Damascus blade had an edge, quite literally, over opponents with European weapons. The superiority wasn't marginal. It wasn't a matter of a slightly better sword in the hands of a skilled fighter. The difference was substantial enough that chronicles mention it, poets wrote about it, and captured blades were considered prizes of war worth more than horses or armor. European swords were fine weapons, but they were simply outmatched. The European blades were, by necessity, compromises. Made softer to prevent shattering, which meant they dulled faster. Made thicker to provide strength, which made them heavier and less quick. Made with more uniform steel, which meant that weak points and strong points were equally distributed. So there were no particular advantages anywhere in the blade. Damascus steel didn't compromise. Or rather, it compromised in ways that produced something greater than the sum of its parts. The secret, though it wouldn't be understood for many centuries, lay in the blade's internal structure. Within the steel existed regions of different hardness. Not random, but organized. Not accidental, but intrinsic to the forging process, though the smiths themselves might not have fully understood why their methods worked. Some regions were very hard, nearly as hard as glass. These regions held the edge, resisted wear, provided the cutting power. Other regions were softer, more ductile, able to absorb energy and distribute stress. These prevented catastrophic failure. Imagine, if you will, a bridge made entirely of rigid steel girders. Strong, certainly, until one connection point fails, and then the entire structure can collapse at once. Now imagine a bridge with some rigid elements and some flexible ones. When stress is applied, the flexible elements absorb and distribute the energy. The rigid elements maintain structure. Together, they create something more resilient than either property alone could provide. This was Damascus steel, a bridge between hardness and toughness, between flexibility and rigidity. When the blade struck something hard, stone, another blade, armor, the impact created stress. In a uniform blade, this stress would concentrate at the weakest point and potentially cause catastrophic failure. A crack would form, and that crack would propagate through the entire structure, following the path of least resistance until the blade broke completely. But in Damascus steel, the stress encountered alternating regions. Hard zones would resist, but if they began to crack, the crack would run into a softer zone that could absorb the energy. The softer zone would deform slightly, dissipating the force, preventing the crack from continuing. The blade would survive what should have destroyed it. This meant that a Damascus blade could take punishment that would shatter European steel. Not just once, but repeatedly. The blade could survive a campaign, a lifetime, generations of use. And there was something else, something visible only under magnification, but critically important. The very edge of a Damascus blade, examined closely, wasn't smooth. It had microscopic serrations, tiny teeth, far too small to see with the naked eye, but present nonetheless. These microserrations weren't damage. They were a feature of the blade's structure, emerging naturally from the same processes that created those alternating hard and soft regions. And they enhanced cutting in a way that wouldn't be fully understood until modern microscopy could examine blade edges in detail. When you cut with a perfectly smooth edge, you're essentially trying to push material apart through pure force. But when you cut with a serrated edge, each tooth acts as a stress concentrator, creating multiple starting points for the cut. It's why a serrated knife cuts bread better than a smooth one, why a saw cuts wood more efficiently than a blade. Damascus steel had these serrations at a microscopic level, too small to feel, too small to see. But when cutting through silk or rope or leather or flesh, they made all the difference. Each tiny tooth helped the cut begin, helped it propagate, helped the material part with less force required. This is partly why the silk scarf test worked. This is partly why Damascus blades seem to cut more efficiently than they should. Not magic, just structure at a scale medieval eyes couldn't perceive. All of these properties, the edge retention, the flexibility, the impact resistance, the cutting power, stemmed from how stress was distributed through the blade. In modern materials science, we talk about stress distribution all the time. We understand that a material's response to force depends not just on what it's made of, but on how that material is structured. A diamond is the hardest natural material on Earth, but hit it with a hammer at the right angle, and it shatters. Glass is very strong in compression, but weak in tension, which is why it breaks so easily when struck. Wood is relatively weak, but its fibrous structure makes it excellent at absorbing impacts. Damascus steel distributed stress better than it should have been possible for medieval metallurgy to achieve. When the blade was struck, or twisted, or bent, the force didn't concentrate in one place. It spread throughout the structure, flowing through hard regions and soft regions, dissipating into the bulk of the metal rather than causing failure at one critical point. This gave the blade a property that modern metallurgists would call impact toughness, the ability to absorb energy from sudden impacts without failing. And remarkably, Tests on surviving Damascus blades have shown that their impact toughness rivals modern alloys. Steels developed with computer modeling and precise temperature control, and an understanding of crystalline structures that medieval smiths couldn't possibly have possessed. Yet somehow, through methods that were part knowledge and part art, part science and part intuition, they achieved it. They created steel that wouldn't be matched in toughness until the Industrial Revolution, until steel mills and modern quality control and metallurgical laboratories. A medieval smith, working with a charcoal forge and a hammer, created metal that could stand beside modern materials. This is extraordinary. This is why Damascus Steel became legendary. And become legendary it did. From the workshops of Damascus and the forges of India, where the steel originated, the reputation of these blades spread across continents. Muslim warriors prized them. Crusaders feared them and coveted them in equal measure. Indian Rajas commissioned them. Persian poets wrote verses about them. European nobles collected them. The blades appeared in chronicles and legends. In the Song of Roland, the greatest knights carry blades that never dull. In Middle Eastern literature, heroes wield swords that can cut through anything. How many of these stories were inspired by actual Damascus blades? How many impossible feats attributed to legendary weapons were actually just Damascus steel, performing exactly as it was designed to? The legend grew with each generation. And unlike many legends, this one was rooted in demonstrable reality. These blades really did perform beyond what seemed possible. The silk scarf test was real. The edge retention was real. The flexibility combined with hardness was real. And then, the knowledge was lost. The methods that created true Damascus steel vanished, sometime around the 18th century. The last smiths who knew the true techniques died without fully passing on their knowledge. The steel from India that made the best blades, Wootz steel, with its particular combination of impurities and carbon content, became unavailable or changed in composition. And suddenly, Damascus steel couldn't be recreated. Smiths tried. They created pattern-welded steel, folding different types of steel together to create similar visual patterns. These blades looked like Damascus steel, but they didn't perform like it. They were beautiful. They were good swords, but they couldn't shatter rock. They couldn't slice silk scarves from the air. They couldn't hold an edge for months without sharpening. The legend remained, but the reality was gone. And for over 200 years, Damascus steel existed only in museums and private collections, in surviving blades passed down through families, in stories and speculation. What made it work? How did medieval smiths create steel that rivaled modern alloys? What were they doing, perhaps without fully understanding what they were doing, that produced such extraordinary properties? These questions haunted metallurgists and historians. And slowly, piece by piece, using modern technology and ancient samples, the mystery began to unravel. But that is a story for another segment. For now, simply rest with the image of a Damascus blade. Pattern-rippled steel, sharp enough to slice falling silk, tough enough to shatter stone, flexible enough to bend and return true. A legend that was real, a mystery that defied physics, until physics finally caught up. Sometimes the most intriguing part of a legend is discovering that the name itself is a misconception. A beautiful irony written into history. We speak of Damascus steel. We imagine the forges of Damascus, Syrian craftsmen hammering glowing metal, the secrets guarded within that ancient city's walls. But here's the remarkable truth. Damascus steel wasn't made in Damascus. Not really. Not where it began. The steel itself, the miraculous metal with its impossible properties, came from somewhere else entirely. Somewhere thousands of miles away, across deserts and mountains and seas. The story of Damascus steel is really the story of Indian Wootz, and of trade routes that connected distant civilizations in ways that still shape our world today. Let us travel back, far back, beyond the medieval period, beyond the Crusades, beyond even the rise of Islam. Back to ancient India, centuries before the Common Era began. Around 300 years before the birth of Christ, in the southern regions of the Indian subcontinent, metallurgists were developing something extraordinary. They called it woods. The word itself may derive from aku, a term in Kannada and Telugu languages meaning steel, or perhaps from wuk, a Sanskrit term. The exact etymology is lost to time, like so much else. But the substance was very real. Woods was crucible steel. To understand what this means, we need to step into the world of ancient metallurgy for a moment. Steel, you see, is iron with carbon added. But the amount of carbon and how it's distributed makes all the difference. Too little carbon, and you have wrought iron, relatively soft, easily worked, but unable to hold a keen edge. Too much carbon, and you have cast iron, hard but brittle, prone to shattering. Steel occupies the middle ground. Enough carbon to be hard and hold an edge, but not so much that it becomes brittle. The challenge for ancient metallurgists was achieving the right balance and, crucially, distributing that carbon evenly through the iron. The Indian solution was ingenious. They placed iron and carbon-rich materials, often wood or leaves, into a sealed clay crucible, a container about the size of a small pot. This crucible was then heated to extreme temperatures in a charcoal-fired furnace. As the temperature rose, the iron melted. The carbon from the organic materials dissolved into the molten metal. And in that sealed environment, protected from oxygen, away from impurities, something remarkable happened. The molten steel slowly cooled within the crucible, and as it cooled, its internal structure organized itself in particular ways. Carbon atoms arranged themselves in patterns. Carbide formations emerged. Grain boundaries formed, all at a microscopic level, invisible to the eye, but fundamental to the steel's properties. When the crucible was finally broken open, what emerged was an ingot. A small cake of steel, perhaps the size of a hockey puck, weighing a pound or two. Unremarkable to look at, just a dark, rough disc of metal. But within that ingot was the potential for legendary blades. This process was being refined in India, while Rome was still a republic, while the Great Wall of China was being built, while the Library of Alexandria still stood. 300 years before the Common Era, give or take, Indian metallurgists were creating steel that wouldn't be matched in quality for over 2,000 years. Think about that for a moment. 2,000 years. Empires rose and fell. Technologies advanced. Human knowledge expanded in countless directions. Yet this particular achievement, this specific metallurgical process, remained unsurpassed for millennia. And here's what makes the story even more intriguing. These ingots became trade goods. Woods wasn't just produced for local use. It was valuable enough to be worth transporting enormous distances. Heavy enough to be awkward cargo, yet valuable enough that merchants found it worthwhile to carry these steel cakes across some of the most difficult terrain on Earth. From southern India, particularly from regions around Golconda and from Tamil territories, the Woods began its journey. Imagine the caravan routes, traders loading the ingots onto oxen or camels, alongside spices and textiles and gemstones, moving north and west, following ancient paths that had connected civilizations long before written records began, through the heat of the Deccan Plateau, across the dangerous mountain passes of the northwest, into Persia, that ancient crossroads where east met west, where ideas and goods and peoples mingled and mixed, and from there, spreading further, to the Levant, to Arabia, to the cities that line the eastern Mediterranean coast. Golconda, in what is now Telangana in south-central India, became particularly famous for its steel. The very name Golconda would later become synonymous with wealth and treasure, partly because of the diamonds found in the region, but also because of the steel. The Woods from Golconda was considered among the finest, some particular quality of the local iron ore, or the specific techniques of the local smiths, produced steel that was especially well-suited to blade making. The Tamil regions of southern India also produced exceptional woods. These areas had access to high-quality iron or deposits and had developed their crucible steel techniques over many generations. The knowledge was passed from master to apprentice, refined with each generation, until the process achieved a kind of perfection. But here's what's crucial to understand. these ingots were just the beginning. The Wootz steel, as it came from the crucible, wasn't yet a blade. It was raw material, potential waiting to be realized. The ingot would need to be heated and forged, shaped and worked, before it could become a weapon or a tool. And this is where Damascus enters the story, not as the birthplace of the steel, but as one of the great centers where that steel was transformed into legendary blades. Damascus, the ancient city in Syria, sat at the heart of trade networks. Caravans from India, from Persia, from Arabia, from Egypt, all converged on Damascus. It was a marketplace for the entire known world. And among the goods that passed through Damascus were those precious Wootz ingots. The city's smiths became expert at working this remarkable steel. They developed techniques for heating the ingots to just the right temperature. They learned how to forge the metal without destroying its special properties. They discovered the right ways to shape it, to draw it out into a blade, to create an edge that could slice falling silk. And as their reputation grew, Damascus became synonymous with the blades themselves. Not because the steel was made there, but because the finest blades were finished there. Because Damascus was where raw potential became realized perfection. This is a crucial distinction, one that was lost for centuries. When Europeans encountered these magnificent blades, they called them Damascus steel because that's where they saw them, where they bought them, where they associated them with. The true origin, India, Wootz, the crucible process, was hidden behind layers of trade and middlemen and geographical distance. And this misunderstanding led to further confusion, because Europeans had their own tradition of creating patterned blades. They would take strips of different types of steel, hard steel and soft iron, and forge them together, folding and welding and folding again. This process, called pattern welding, created visible patterns in the finished blade as the different layers showed through. European pattern-welded blades could be beautiful. The Vikings made stunning swords this way, with intricate patterns deliberately created through careful manipulation of the welded layers. These were fine weapons, but they weren't Damascus steel. They didn't have the same properties. They couldn't perform the same feats. Yet because both types of blade showed patterns on their surface, they were conflated. European smiths began calling their pattern-welded blades Damascus steel. The name became confused, applied to two entirely different things. True Damascus, crucible steel forged from Wootz ingots, and European Damascus, pattern-welded blades that merely resembled the originals. This confusion persists even today. Modern knife makers create Damascus blades through pattern welding, and they're beautiful objects, worthy of admiration. But they're not true Damascus steel. They don't have the same internal structure. They don't have those alternating regions of hard and soft steel that emerged naturally from the crucible process. They don't have the carbide formations, the specific grain structures, that gave historical Damascus steel its legendary properties. True Damascus steel, Wootz steel, properly forged, was crucible steel. Melted in a sealed container, cooled slowly, its structure determined by metallurgical processes that happened at the molecular level. The patterns on its surface weren't created by welding different metals together. They emerged from within the steel itself, as natural as the grain in wood or the patterns in a fingerprint. When a smith heated a Wootz ingot and began to forge it, the patterns were already there, waiting to be revealed. As the metal was worked, as the blade took shape, those internal structures would show on the surface. Dark bands and light bands, flowing in organic curves, creating the distinctive watered silk appearance that became Damascus steel's signature. The smith didn't create these patterns. The smith revealed them. This is a profound difference. It meant that the steel's properties and its beauty were intrinsically linked. You couldn't have one without the other. The patterns weren't decoration. They were a visible manifestation of the internal structure that made the blade exceptional. But we're getting ahead of ourselves again. Let's return to those trade networks, to the flow of Wootz from India to the Middle East. Because while Damascus was the most famous center for working this steel, it wasn't the only one. The ingots traveled along multiple routes, creating multiple centers of blade-making expertise. Persian cities became particularly important. Merv, in what is now Turkmenistan, was a major center on the Silk Road. Woods arrived there along with Chinese silks and Central Asian horses, and local smiths developed their own traditions for working it. Yazd, in central Iran, also became known for its blades. The city sat in an oasis on the edge of the Great Salt Deserts, a natural stopping point for caravans. The smiths there had access to woods from India, and also, interestingly, began producing their own crucible steel using local materials. Because here's another fascinating twist in the story. The crucible steel technique spread. Indian metallurgists weren't the only ones who could produce it. The method moved along the same trade routes as the ingots themselves, carried in the minds of traveling smiths, taught and learned, and adapted to local conditions. Khorasan, the great historical region of eastern Persia, became a producer of crucible steel. The region had iron ore, fuel for furnaces, and craftsmen who had learned the Indian techniques and modified them. Khorasan steel developed its own reputation, distinct from Indian woods, but achieving similar properties. Isfahan, the magnificent Persian city that would later become the capital of the Safavid Empire, emerged as perhaps the greatest sword-making hub outside of Damascus itself. Isfahan had advantages. It sat at the convergence of multiple trade routes. It had wealthy patrons who commissioned fine blades, and it accumulated a concentration of master smiths whose skills were passed down through generations. By the medieval period, Isfahan blades were considered equal to those from Damascus. The city's smiths had perfected their understanding of wood steel, how to heat it, how to forge it, how to shape it without destroying its properties. An Isfahan blade was a treasure, a symbol of status, a weapon that could change the course of a battle. And all of this, Damascus, Isfahan, Merv, Yazd, all of these centers of blade making existed because of those ingots from India. Because of wood steel that had been perfected centuries earlier, thousands of miles away, and that traveled along trade routes that connected the ancient world in ways that still seem remarkable today. These trade networks were the lifeblood of Damascus Steel. Without them, without the ability to transport those heavy ingots across such vast distances, the legendary blades could never have existed. Trade made it possible. Commerce, exchange, the movement of goods and ideas across borders and cultures and civilizations. The Indian metallurgists provided the steel. The Persian and Syrian smiths provided the craftsmanship. Together, separated by thousands of miles but connected by trade, they created objects that would be treasured for centuries, that would inspire legends, that would eventually give rise to one of history's great metallurgical mysteries. Because, and this is the heart of the tragedy, the knowledge was fragile. The wood's production in India depended on specific ores, specific techniques, specific knowledge passed from master to apprentice. The forging techniques in Damascus and Isfahan depended on the accumulated wisdom of generations of smiths, understanding gained through experience and observation, and careful attention to the behavior of the steel. None of this was written down in comprehensive form. Metallurgy was guild knowledge, trade secrets, the kind of information that was guarded jealously and transmitted orally. A master smith might show an apprentice how to judge the color of heating steel, how to tell when it reached the right temperature for forging, but he wouldn't explain the underlying principles because he didn't know them. He knew that steel of a certain color behaved a certain way. That was enough. This worked, as long as the chain of transmission remained unbroken, as long as each generation successfully trained the next, as long as the raw materials remained available, as long as the trade networks functioned. But nothing lasts forever. Political changes disrupted trade routes. Wars and invasions scattered craftsmen. The sources of high quality ore in India became depleted or were lost as knowledge about their exact locations faded. The very specific conditions that made wood steel possible, the right ore, the right carbon sources, the right temperatures, the right cooling rates, proved impossible to maintain indefinitely. By the 18th century, true wood's production had ceased. The last smiths who knew how to properly forge it had died. The ingots that remained were treasured, worked carefully by smiths who knew they were irreplaceable. And when those last ingots were gone, that was it. Damascus Steel, the genuine article, could no longer be made. What survived were the blades themselves. Thousands of them, scattered across the world, in museums and private collections and family treasures. Beautiful objects, still functional, still sharp even after centuries. Silent witnesses to a lost art. And what survived were the stories. The legends of blades that could perform impossible feats. Tales that seemed to grow in the telling, but that, it turned out, were rooted in truth. These blades really were exceptional. They really did things that other blades couldn't match. But how? That question would haunt metallurgists for centuries. How did ancient smiths, working with primitive equipment, create steel that rivaled modern alloys? What was happening inside the metal at a level they couldn't see or measure? What secrets were locked inside those watered patterns that flowed across the blade's surface? The answers would require modern science. Electron microscopes, X-ray diffraction, crystallography, tools and techniques that wouldn't exist until centuries after the last true Damascus blade was forged. But even before those tools existed, even in the darkness of not knowing, the blades themselves remained. Physical evidence, proof that it was possible, inspiration for metallurgists who dreamed of recreating what was lost. And so the mystery deepened. The legend of Damascus Steel, steel that wasn't from Damascus, made from ingots that traveled thousands of miles, worked by smiths who didn't fully understand what made it special, persisted, waiting for science to catch up, waiting for human understanding to finally grasp what ancient craftsmen had achieved through intuition and experience and generations of accumulated wisdom. But that story, the story of rediscovery, of scientific investigation, of finally understanding what made Damascus Steel legendary, that will have to wait for another time. For now, rest with the image of those trade routes. Caravans carrying small, heavy ingots across deserts and mountains. Indian woods traveling to Persian forges and Syrian workshops. Steel born in one place, perfected in another, becoming legendary everywhere. A testament to human ingenuity and to the connections that bound the ancient world together in ways we're still discovering today. There is something almost alchemical about the ancient process of creating wood steel. Fire and earth, metal and time, all coming together in ways that transformed raw materials into something extraordinary. Tonight, let us slow down. Let us enter the world of the ancient metallurgist and understand, step by careful step, how wood steel came into being. Imagine, if you will, a workshop in southern India. Perhaps it's near Golconda, or in the Tamil regions where the craft reached its highest refinement. The date is uncertain. It could be 2,000 years ago, or 1,000, or 500. The process remained largely unchanged across centuries, perfected early, and then maintained with careful conservatism. Because when you've discovered something that works this well, you don't tamper with it lightly. The metallurgist, let's call him that, though he might have been known by a different title, begins with raw materials. Iron, first and foremost. Not pure iron, which doesn't exist in nature, but iron ore. Perhaps magnetite, perhaps hematite, the black or red stones that ancient peoples learned to recognize as the source of metal. This ore has been mined, perhaps from nearby deposits, perhaps from sources known to produce the best quality iron. The ore has already been processed through an initial smelting, reduced from stone to a more workable form. What the metallurgist has before him might be bloom iron, a spongy mass of iron with slag still trapped within it. Or it might be pieces of wrought iron that have been further refined. Different sources describe different starting points, and the truth is that techniques varied by region and era. But all roads lead to the same destination, iron that will be transformed into steel. Alongside the iron, the metallurgist prepares his other crucial ingredient, carbon. But not pure carbon. That's too difficult to obtain, and besides, not necessary. Instead, he uses organic matter, wood often, specifically, pieces of certain trees that have been carefully selected. Some sources mention leaves. Others speak of charcoal dust, or pieces of bamboo, or other plant materials rich in carbon. The choice of carbon source mattered, though the ancient metallurgists might not have understood precisely why. Different plants contain different additional elements in trace amounts. The wood from one tree might have slightly more manganese, or phosphorus, or sulfur than another. These trace elements, in tiny, almost homeopathic quantities, would affect the final steel's properties in subtle but important ways. So our metallurgist has his iron. He has his carbon source. Now comes the vessel that gives crucible steel its name, the crucible itself. These were small containers, typically made of clay. Not just any clay, but clay carefully chosen and prepared, mixed with sand or other materials to make it refractory, able to withstand extreme heat without cracking or melting. The crucibles were about the size of a modern coffee mug, perhaps slightly larger, small enough to be manageable, large enough to produce a useful amount of steel. The inside of the crucible would be coated, sometimes with a layer of material that would help protect the molten steel from contamination. Some sources mention glass flux being added, silica-based materials that would form a protective layer on top of the molten metal, shielding it from oxygen and preventing oxidation. Into this prepared crucible, the metallurgist places his ingredients. The exact recipe varied, but a typical charge might include pieces of bloom iron or wrought iron, pieces of his chosen carbonaceous plant material, and perhaps a small amount of that glass flux. The proportions were critical. Too much carbon, and the resulting steel would be too brittle. Too little, and it wouldn't be hard enough to hold an edge. But here's what's remarkable. The metallurgist determined these proportions not through chemical analysis or precise measurement, but through experience. He knew that a crucible filled to this level with iron, and this much wood, produced good steel. He might not know why, in terms of carbon percentages or molecular structures, but he knew what worked. The crucible, now loaded with its charge, is sealed. A lid of clay is fitted over the top, sometimes cemented in place with more clay to ensure an airtight seal. This sealing is absolutely crucial. If oxygen reaches the molten metal, it will oxidize, forming iron oxide, rust, essentially, and ruining the steel. The sealed crucible creates a reducing atmosphere, where carbon monoxide and other gases protect the metal from oxidation. Now the crucible, sealed and ready, is placed into the furnace. These furnaces were marvels of ancient engineering in their own right. Some were built into hillsides to take advantage of natural draft. Others were freestanding structures, carefully designed to achieve and maintain extremely high temperatures. The fuel was typically charcoal, would burn down to pure carbon, which burns hotter and cleaner than raw wood. The crucibles might be buried in this charcoal, surrounded by fuel, heated from all sides. Or they might be placed in a chamber above the main fire, heated by the rising flames and hot gases. And then, the waiting begins. This is where patience becomes paramount. The furnace must be brought up to temperature gradually. Too fast, and the crucible might crack from thermal shock. The charcoal is lit. Air is supplied, perhaps through bellows, perhaps through clever design that channels natural wind. The temperature rises, and rises, and rises. The target temperature is somewhere above 1,500 degrees Celsius. That's 2,732 degrees Fahrenheit. Hot enough that the iron melts. Hot enough that carbon begins to dissolve into the molten iron. Hot enough that the very specific chemical reactions necessary for creating what steel can occur. In India, the monsoon winds played a role. These powerful, consistent winds could be channeled through furnace designs, providing a steady supply of air that maintained the high temperatures. It's one of those beautiful intersections of geography and technology. The climate itself became part of the metallurgical process. During monsoon season, when the winds were most reliable, steel production could proceed most efficiently. Reaching 1,500 degrees Celsius with a charcoal furnace is no simple feat. Modern steel mills use sophisticated temperature controls and powerful burners. Ancient metallurgists had observation and experience. They might judge temperature by color, the precise shade of orange or yellow-white that the crucible glowed. They might judge by the behavior of the fire, the sound it made, the way the heat felt on their faces. And once that temperature was reached, the waiting continued. Because the smelting process, the transformation of iron and carbon into Wootz steel, took time. Not minutes. Not an hour or two. The sources speak of processes lasting anywhere from 6 hours to 6 days, depending on the specific technique and the desired outcome. 6 hours at minimum. Think about that. 6 hours of maintaining temperature above 1,500 degrees Celsius. 6 hours of feeding fuel, of monitoring the fire, of ensuring that conditions remain stable. This wasn't something you could walk away from. This required constant attention, skill, and endurance. And some processes took far longer. 6 days. Nearly a week of continuous firing. Multiple shifts of workers, watching over the furnace day and night, keeping the temperatures high, the conditions perfect. This wasn't mass production. Each batch was an investment of enormous labor and resources. But the time was necessary. Inside that sealed crucible, transformations were occurring. The iron was melting, becoming liquid. The carbon from the plant materials was dissolving into that molten iron. But it wasn't just mixing uniformly. The cooling and reheating, the precise temperature gradients, were creating specific crystalline structures. Carbide formations were nucleating. Grain boundaries were forming. The woody biomass did more than just provide carbon. As it heated and partially combusted in the low-oxygen environment, it released gases. Carbon monoxide, hydrogen. These gases helped maintain the reducing atmosphere inside the crucible, protecting the steel from oxidation. They might have also affected the chemistry of the steel in subtle ways, introducing trace elements or affecting how the carbon distributed itself through the iron matrix. In some regions, metallurgists added other materials. Glass flux, as mentioned before, silica that would melt and form a protective layer. Some recipes, documented by medieval scholars, speak of mixing cast iron, very high carbon iron that's been melted and cast into molds, with bloom iron, which has lower carbon content. By combining these two forms of iron in specific proportions, the metallurgist could achieve exactly the right carbon percentage in the final steel. The medieval Persian scholar al-Biruni documented some of these recipes in the 11th century. He was a polymath, interested in everything from astronomy to mineralogy, and he took the time to record what he observed about steelmaking. His descriptions mention mixing hard cast iron with softer iron, heating them together until they unified. These medieval recipes might have been variations on even older techniques, or they might have been innovations developed in Persia after learning the principles from Indian metallurgists. But let's return to our workshop, where the crucible has been in the furnace for hours, or perhaps days. Eventually, the metallurgist judges that the process is complete. The carbon has fully dissolved. The steel has formed. Now comes one of the most critical phases, the cooling. The crucible cannot simply be removed from the furnace and allowed to cool in open air. That would be disastrous. The sudden temperature change would cause the steel to crack, or would create internal stresses that would make it unworkable, or would produce a crystalline structure entirely unsuitable for blade making. No, the cooling must be slow, carefully controlled. The crucible might be buried in warm sand or ash, or it might be left in the furnace as the fire gradually dies down over many hours. Or it might be moved to a special cooling chamber where temperature could be reduced gradually over a day or more. This slow cooling is what allows the internal structure of the steel to organize itself properly. As the molten steel solidifies and cools, carbon atoms have time to find their preferred positions in the crystal lattice. Carbide particles, iron carbide, also called cementite, form and arrange themselves in particular patterns. Different regions of the ingot develop different characteristics, creating those alternating zones of hardness and toughness that make Damascus steel exceptional. If cooled too quickly, all of this would be disrupted. The carbon wouldn't have time to organize. The crystal structures would be chaotic, stressed, full of defects. The resulting steel would be disappointing at best, useless at worst. And sometimes, despite all precautions, despite all skill and experience, an ingot would fail. Perhaps contamination had entered the crucible. Perhaps the temperature hadn't been maintained correctly. Perhaps some subtle aspect of the process had gone wrong in ways the metallurgist couldn't have predicted or prevented. These failed ingots weren't simply discarded. Steel was too valuable, represented too much labor and resources to throw away. Instead, they were recycled. A failed ingot could be broken up and used as the iron source for a new batch. Placed into a fresh crucible with new carbon sources, sealed, and heated again. The steel could be remade, given another chance to achieve the proper structure. This recycling wasn't just practical efficiency. It also suggests something about the nature of Woot's steel production. The metallurgists understood, at least empirically, that steel could be remade. That its properties weren't fixed, but depended on process. Heat it correctly, cool it correctly, and even failed steel could be transformed into something exceptional. When a batch was successful, when the slow cooling was complete, and the crucible finally opened, what emerged was the precious ingot. A small cake of steel, perhaps weighing a pound or two. Its surface would be rough, bearing the texture of the crucible's interior. It would be dark, unremarkable to the uninformed eye. But to someone who knew, to someone who understood what this small piece of metal represented, it was treasure. But even now, the process wasn't complete. Because this ingot, though it contained the potential for a legendary blade, still needed to be forged into shape. And forging introduced new stresses, new challenges. When the ingot was heated and hammered, when it was drawn out into a blade shape, enormous physical stresses were introduced into the steel. The crystal structure was being deformed. Internal tensions developed. If these tensions weren't relieved, they could cause the blade to crack, or to warp as it cooled, or to fail in use. So there was another step, tempering rooms. Chambers where forged blades were kept at elevated temperatures for extended periods, allowing internal stresses to gradually relieve themselves. The steel could relax, in a sense. The strains introduced by forging could partially undo themselves, reaching a new equilibrium that was more stable. This might take days. The blade would rest in a warm environment, perhaps heated by residual warmth from forges, gradually cooling from forging temperature to room temperature over an extended period. No rushing, no shortcuts, just time and patience, and understanding that steel needed this rest to achieve its full potential. All of this, the careful selection of materials, the precise loading of crucibles, the long hours of high-temperature heating, the controlled cooling, the stress relief, all of this was chemistry and physics. Not magic, not mystery, though it might have seemed mysterious to those who didn't understand the underlying principles. And here's what's crucial. This was not folding. This was not pattern welding. No one was taking different pieces of metal and welding them together. No one was folding steel back on itself hundreds of times, as Japanese swordsmiths did with their different techniques, or as European smiths did when creating pattern-welded blades. The patterns in Damascus steel, those beautiful waves and swirls on the blade's surface, emerged from within the steel itself. They were a manifestation of the steel's internal crystalline structure, created through chemistry and careful heat treatment. The alternating bands of different hardness, the carbide formations, the grain boundaries, all of these formed through the crucible process and the subsequent forging, not through mechanical manipulation of layered metals. This is why true Damascus steel could never be recreated through pattern welding. Pattern welding creates superficial similarity, visual patterns that can be quite beautiful, but it doesn't replicate the internal structure. It doesn't create those microscopic carbide formations, those specific crystal arrangements that gave historical Damascus steel its legendary properties. Chemistry created Damascus steel. The right iron, with specific trace elements. The right carbon, added in the right amounts. The right temperatures, maintained for the right duration. The right cooling rates. The right forging techniques. All of these factors, working together, produced steel with properties that seemed impossible. And the remarkable thing is that ancient metallurgists achieved this without understanding the chemistry. They couldn't have explained crystal structures or carbide formations. They didn't know about iron-carbon phase diagrams or grain boundary strengthening. They worked through observation and experience, through trial and error across generations, until they found methods that worked consistently. They learned to read the steel, to judge by color and sound, and feel when conditions were right, to recognize a successful ingot by its appearance and how it responded to initial forging, to understand, in ways that couldn't be put into words, but only demonstrated and taught through apprenticeship, how to coax from earth and fire and time something that approached perfection. This is the art within the science, the human element in a process that we can now explain through chemistry and physics. Ancient metallurgists were, in their own way, brilliant chemists and material scientists. They just used a different language, a different way of knowing, than modern scientists employ. And when the technique was lost, when the last master metallurgists died without fully transmitting their knowledge, it took modern science, with all its instruments and theories and analytical capabilities, centuries to figure out what had been lost, to rediscover what ancient craftsmen had known how to do, even if they couldn't have explained it in modern terms. The ingots they created, through this complex, time-consuming, demanding process, were the foundation of the legend. Everything else, the forging into blades, the shaping and sharpening, the tests of cutting silk or shattering stone, all of that depended on starting with steel that had been made correctly. Steel that contained within its crystalline structure the potential for excellence. From crucibles in Indian workshops, these ingots traveled the world, carried by merchants, transformed by smiths, becoming the weapons and tools that would make Damascus Steel famous. But it all began here, with fire and patience, with chemistry that ancient metallurgists understood through their hands and eyes, even if they couldn't explain it through equations. Rest now with the image of that opened crucible, the rough ingot within its still radiating heat. Potential waiting to be realized. Metal that has been transformed, through human ingenuity and careful craft, into something extraordinary. The first step in a journey that would end with blades sharp enough to slice falling silk, tough enough to shatter rock, legendary enough to inspire wonder for centuries to come. There is something deeply human about our response to patterns. We see them everywhere. In the rings of a tree, in the swirls of a fingerprint, in clouds and coastlines, and the spiral of a nautilus shell. Patterns draw the eye, suggest order, hint at hidden meanings. And perhaps no patterns in metallurgical history have captured the imagination quite like those that flow across the surface of Damascus steel. Tonight, let us explore these patterns. Not just what they looked like, but what they were, where they came from, why they formed, and what they reveal about the steel itself. Because these weren't decorations. They weren't added for beauty, though beautiful they certainly were. These patterns emerged naturally from the steel's internal structure, as inevitable as waves on water, as fundamental as the grain in wood. The patterns were called damask by Europeans who first encountered them, after Damascus, the city where the blades were most commonly seen. The comparison was to damask fabric, woven textiles with patterns created through the interplay of different threads, creating surfaces that seemed to shimmer and shift depending on how light struck them. Damascus steel had this quality. The patterns seemed to move, to flow, to possess an almost liquid quality despite being frozen in solid metal. Waves and swirls, lighter bands and darker bands interweaving across the blade's surface in organic curves that no two blades shared identically. Each blade was unique, its patterns as individual as a fingerprint. But what were these patterns? What, exactly, was creating this visual effect? The answer lies in something called impurity segregation. Now, impurity might sound negative, but in metallurgy, impurities aren't necessarily bad. They're simply elements other than the primary metal. In this case, elements other than iron. And in Wootz steel, these impurities played a crucial role in creating both the patterns and the steel's exceptional properties. Remember that Wootz steel was made from iron ore, which naturally contains trace amounts of other elements. Manganese, phosphorus, sulfur, silicon, tiny amounts, sometimes less than 1%, sometimes even less than 0.1%. But these traces were enough. When the steel was melted in the crucible, when it cooled, when it was later forged, these trace elements didn't distribute themselves uniformly. They segregated. Imagine oil droplets in water. They don't mix uniformly. They separate, they cluster, they form distinct regions. Something similar happened with the trace elements in Wootz steel. As the molten steel cooled in the crucible, as the iron crystallized, these impurities were pushed to certain locations. Some regions became slightly enriched in phosphorus. Other regions had slightly more sulfur. Still others had different concentrations of manganese or other elements. These variations created regions of slightly different composition throughout the steel. And these compositional differences affected how the steel behaved during forging, and crucially, how it appeared after polishing. But the patterns weren't just about impurities. They were also about carbides, specifically iron carbide, also called cementite. This is the hard, crystalline compound formed when carbon combines with iron. In Damascus steel, the cementite didn't form a uniform distribution. It organized itself into structures, into arrangements, into patterns. During the forging process, when the smith heated the ingot and hammered it, when he drew it out into a blade shape, the internal structure of the steel responded. The repeated heating and cooling, hot when being worked, cooling between forging sessions, caused the cementite to arrange itself in particular ways. Think of it like this. Imagine you have a deck of cards scattered randomly across a table. Now imagine you start tapping the table rhythmically. Some cards begin to align, to form patterns, organized by the vibrations. Something analogous happened with the carbides in Damascus steel during forging. The repeated thermal cycling, hot, cool, caused the cementite particles to migrate, to cluster, to form what metallurgists call planar arrays. Planar arrays are essentially flat sheets or layers of particles. In Damascus steel, spherical or near-spherical particles of cementite arranged themselves into these sheet-like formations. These sheets weren't perfectly flat. They curved and flowed, following the contours created by the forging process. When the blade was forged, when metal was stretched and compressed and moved, these sheets of carbides moved with it, creating those flowing, wavy patterns. The sheets were oriented in particular directions, aligned by the way the metal flowed during forging. Where the smith hammered harder, or stretched the metal more, the patterns would be elongated, stretched out. Where the metal was less worked, the patterns might be more compact, more tightly clustered. And here's something remarkable. Even if the pattern was temporarily disrupted, it could restore itself. This phenomenon is called Ostwald ripening, named after the German physical chemist Wilhelm Ostwald, who studied how particles evolve in solutions and solids. Ostwald ripening describes how smaller particles tend to dissolve and redeposit onto larger particles over time. In Damascus steel, if the blade was heated again after forging, perhaps for hardening or tempering, the cementite particles could migrate. Smaller ones would dissolve back into the iron matrix, and their carbon would migrate to larger cementite particles, making them grow. But here's the crucial part. This growth wasn't random. The carbides tended to grow back along the same planar arrays where they'd been before. The pattern had a kind of memory, encoded in the steel structure. So even if forging or heat treatment partially erased the pattern, it could re-emerge with subsequent heating and cooling cycles. The pattern wanted to exist, in a sense. It was the energetically favorable configuration for the carbides in this particular steel composition. Now, remember those impurities we mentioned earlier? Phosphorus and sulfur in particular played a special role in the patterns. These elements didn't just segregate randomly. They tended to concentrate in particular regions, and these regions guided where carbides would form. Phosphorus has an interesting property. It's only slightly soluble in iron. When molten steel cools, phosphorus tends to be pushed out ahead of the solidification front, concentrating in the regions that solidify last. This creates phosphorus-rich bands, or regions, in the solidified steel. These phosphorus-rich regions became nucleation sites for carbides. When the steel was heated during forging, when conditions were right for carbides to precipitate out of the iron matrix, they preferentially formed in these phosphorus-rich areas. The phosphorus acted like a template, guiding where the carbides would appear, reinforcing the patterns. Sulfur played a similar role, though through different mechanisms. Sulfur tends to form compounds with iron and other elements, creating inclusions, tiny particles of non-metallic materials embedded in the steel. These inclusions also influenced carbide formation and contributed to the visible banding. The combination of these effects, impurity segregation, carbide formation, phosphorus and sulfur concentration, the repeated thermal cycling of forging, all work together to create the distinctive patterns. Multiple factors, operating at microscopic and even atomic scales, combining to produce something visible to the naked eye. But there's another layer to this story, because when a Damascus blade was first forged and shaped, when it came off the smith's anvil, the patterns weren't necessarily visible. The surface was rough, covered with forged scale, the black iron oxide that forms on hot steel. Even after the scale was removed, even after initial polishing, the patterns might be subtle or barely visible. To reveal the patterns fully, to make them stand out in the dramatic fashion that Damascus steel is famous for, the blade needed to be etched. Acid etching, a weak acid, perhaps vinegar, perhaps a mixture of acidic plant juices, perhaps other traditional solutions, would be applied to the polished steel surface. The acid attacked different regions of the steel at different rates. The phosphorus-rich regions, the sulfur-containing regions, the areas dense with carbides, these all reacted differently to the acid. Some areas would etch more deeply, appearing darker. Other areas would resist etching, remaining brighter. The contrast between these regions made the patterns visible. This etching was traditionally done after the blade was finished and polished. A smith might polish the blade to a mirror finish, then carefully apply acid, watching as the patterns emerged like a photograph developing. The longer the etching continued, the more pronounced the contrast became. The smith had to judge when to stop, when the patterns were clear, but the surface hadn't been roughened too much by over-etching. And here's something that speaks to the stability of these patterns. They were permanent. Well, perhaps not quite permanent. Nothing truly is, but remarkably stable. You could polish the blade again, removing the etched surface, and the patterns would disappear. But etch it again, and they would return, exactly as before. The patterns weren't just on the surface. They extended throughout the steel. Polishing removed surface metal, but the underlying structure remained. Re-etching simply revealed that structure again. You could do this repeatedly, polish, etch, and the patterns would keep coming back unchanged, because they were fundamental to the steel's internal architecture. This permanence was part of what made Damascus patterns so valued. They weren't like decorative engraving that could wear away, or like gilding that could flake off. They were intrinsic. As long as any metal remained, the pattern remained within it. Different blade-making centers developed distinctive pattern styles. Damascus blades often showed one characteristic pattern. Isfahan blades might show another. These weren't conscious design choices, in the sense of a modern manufacturer choosing a logo. Rather, they emerged from slightly different steel compositions, slightly different forging techniques, slightly different traditions of working the metal. A smith in Damascus, trained in his city's particular methods, would produce blades whose patterns reflected those methods. The patterns became signatures, not intentional but inevitable. An expert could look at a blade's pattern and potentially identify where it was made, who might have made it, even roughly when it was made, based on the characteristics of the patterns and how they compared to known examples. But, and this is crucial to understand, the patterns were a side effect. They weren't the goal. The goal was to create steel with exceptional properties: hardness, toughness, edge retention, flexibility. The patterns emerged as a natural consequence of the internal structure that produced those properties. The carbide formations that created the visible patterns were the same carbide formations that made the blade hard. The phosphorus-rich regions that guided pattern formation also affected how the steel hardened and tempered. The impurity segregation that created visual contrast also created the alternating zones of different hardness that gave the blade its toughness. Form followed function. Beauty emerged from utility. The patterns were proof that the steel had been made correctly, that the internal structure was right. A blade without patterns might still be functional, but it likely wasn't true Damascus steel. The patterns were diagnostic, revealing in visible form what was happening at microscopic scales throughout the metal. This is why you couldn't create true Damascus steel simply by engraving patterns on ordinary steel, or by acid etching patterns onto a blade's surface. Those would be purely cosmetic, superficial. They might look similar from a distance, but they wouldn't be the same. They wouldn't reflect the internal structure. They wouldn't be accompanied by the exceptional mechanical properties. And this is also why pattern-welded blades, despite their beauty, weren't true Damascus steel. Pattern welding creates patterns through mechanical layering, welding different steels together, folding them, manipulating them. The resulting patterns are visible and can be quite striking, but they're created differently, and the steel's properties are different. Pattern-welded steel can be excellent in its own right, but it's not the same as crucible steel with naturally emergent patterns. Modern attempts to recreate Damascus steel had to reproduce not just the visual patterns, but the underlying structure that created them. It wasn't enough to make something that looked like Damascus steel. It had to be Damascus steel, with the same composition, the same carbide formations, the same impurity segregations. Only then would it have the same properties. Only then would the patterns be real, rather than replicated. Think about what this means for the ancient smiths. They were working without microscopes, without chemical analysis, without any way to see what was happening inside the steel at microscopic scales. Yet they developed methods that produced these complex internal structures consistently. They learned to recognize successful steel by its patterns, understanding empirically that certain pattern characteristics correlated with certain performance characteristics. A master smith might teach an apprentice to look for particular types of waves in the pattern, particular densities of banding, particular contrasts between light and dark regions. Steel that looks like this, he might say, will make a blade that performs like this. Practical knowledge, accumulated over generations, encoded in visual patterns that could be seen and judged. The patterns were a window into the invisible. They made the microscopic visible. They allowed smiths to quality control their product using only their eyes and experience, judging internal structure by external appearance. And for modern metallurgists trying to understand Damascus steel, trying to reverse engineer centuries-old techniques, the patterns were clues. Each blade was a frozen record of its own making. The patterns contained information about the steel's composition, its thermal history, how it had been forged. Reading these patterns correctly, understanding what they revealed about internal structure, was key to eventually recreating the lost art. But we're moving ahead of ourselves again. For now, simply rest with the image of a Damascus blade, freshly etched, its patterns emerging from beneath the polish. Waves of light and dark flowing across the steel like water frozen mid-motion. Beautiful, yes, but more than beautiful. Meaningful. Each swirl and band a testament to chemistry and physics operating at scales too small to see, creating something that became legend. The patterns that gave Damascus steel its name, its identity, its visual mystique. They were never decoration. They were revelation. The steel, speaking in the only language it had, showing those who knew how to look exactly what it was, exactly how it was made, exactly why it was extraordinary. Sometimes the most profound discoveries are made when we look at old things with new eyes. When technologies advance to the point where we can finally see what was always there, hidden in plain sight, waiting for human understanding to catch up. And few discoveries in materials science have been quite as startling, quite as paradigm-shifting, as what researchers found when they examined Damascus steel with modern electron microscopes at the turn of the 21st century. What they found was impossible. Or rather, it should have been impossible. Ancient smiths, working over 1,000 years ago, had created something that modern scientists had only recently discovered, had only recently learned to manufacture deliberately, and had certainly never expected to find in medieval metalwork. They found nanotechnology, in steel forged before the scientific method existed. in blades made centuries before anyone knew that atoms existed, let alone how to manipulate structures at the atomic scale. Let us explore this revelation slowly, carefully, because it changes everything we thought we understood about Damascus Steel and about the boundaries between ancient craftsmanship and modern science. The discovery came in the early 2000s, when a team of researchers led by Peter Pofler at the Technical University of Dresden in Germany decided to examine Damascus steel using transmission electron microscopy. This isn't ordinary microscopy. This is technology that uses beams of electrons rather than light, that can magnify objects by millions of times, that can reveal structures at the atomic level. They were looking for the source of Damascus steel's exceptional properties. They knew about the carbides, about the impurity segregation, about the patterns. But they suspected there was more to the story, something happening at scales too small for previous analysis techniques to have detected. What they found were carbon nanotubes, embedded within the steel matrix. Structures that modern materials scientists had only recently learned to synthesize, that were at the cutting edge of nanotechnology research, that represented some of the most advanced materials engineering of the modern era. And here they were, in steel made over a millennium ago, by smiths who had no concept of nanoscale structures, no electron microscopes, no theoretical framework for understanding what they were creating. Let's pause for a moment and understand what carbon nanotubes are. Imagine a sheet of carbon atoms, arranged in a hexagonal pattern like chicken wire, each carbon atom bonded to 3 neighbors. Now imagine rolling that sheet into a tube, a cylinder, with the carbon atoms forming the walls of the tube. The tube is hollow, the walls are exactly 1 atom thick, and the tube is incredibly, almost unimaginably small. How small? The nanotubes found in Damascus steel measured between 0.5 and 80 nanometers in diameter. A nanometer is 1/1000th of a meter. To put that in perspective, if you enlarged a nanometer to the size of a marble, then a marble would be enlarged to the size of the Earth. These are structures operating at scales that dwarf even bacteria, structures smaller than most viruses, structures that exist in a realm where quantum mechanics begins to matter more than classical physics. Millions of these nanotubes could fit side by side across the head of a thumbtack. Millions. The entire elaborate structure, invisible to any microscope that ancient smiths could have imagined, hidden within what seemed to be solid steel. And it wasn't just carbon nanotubes. The researchers also found cementite nanowires. These are similar structures, but made of iron carbide, that same cementite we discussed earlier as forming the hard regions in Damascus steel. But these weren't the normal carbide formations. These were nanowires, elongated crystalline structures, incredibly thin, stretching through the steel matrix like threads woven through fabric. These nanowires were also measured in nanometers, single-digit nanometers in diameter in some cases, so thin that if you lined up 1,000 of them side by side, they still wouldn't span the width of a single human hair. The implications were staggering. Carbon nanotubes are among the strongest materials known to science. In pure form, they have a tensile strength, the ability to resist being pulled apart, that exceeds that of steel by orders of magnitude. A single nanotube, scaled up to the size of a steel cable, would be dozens of times stronger. They're also extraordinarily flexible, able to bend and stretch in ways that bulk materials cannot. Cementite nanowires, while not as strong as carbon nanotubes, are still impressive structures. They provide hardness, where resistance, the ability to maintain a sharp edge. But normally, cementite is brittle. In bulk form, it can crack and fracture under stress. Brittleness is the price you pay for hardness. But not here. Not in Damascus steel. Here, the cementite nanowires were protected, embedded in the softer iron matrix, distributed throughout the steel in ways that prevented catastrophic failure. The nanowires were there, providing hardness and strength, but they couldn't crack and propagate fractures through the entire blade because they were isolated, separated by regions of tougher material. This is a fundamental principle of composite materials. Modern engineers create composites by combining materials with different properties. Hard particles in a soft matrix, or stiff fibers in a flexible resin. The composite has properties that neither component has alone. Strength without brittleness. Hardness without fragility. Damascus steel was a nanocomposite, created accidentally through traditional techniques, but nonetheless a composite material with reinforcing structures at the nanoscale. Ancient smiths had achieved what modern materials scientists strive for: a material that was simultaneously hard and tough, strong and flexible, combining properties that normally exclude each other. But how? How did these nanostructures form? Carbon nanotubes don't just appear spontaneously. Modern synthesis requires carefully controlled conditions, specific temperatures, catalysts, gas mixtures. How could a medieval smith, working with charcoal and clay crucibles, possibly create them? The answer lies in those trace elements we discussed earlier, and in the specific conditions inside the crucible during steel production. Remember that wood and plant materials were added as the carbon source. These organic materials, as they heated and partially burned in the low-oxygen environment, released a variety of compounds, carbon-containing gases, trace amounts of other elements. Some of these trace elements, perhaps vanadium or cobalt or nickel in minute quantities, could act as catalysts. At the high temperatures inside the crucible, these catalysts could promote the formation of carbon nanotubes. The carbon atoms, freed from the decomposing plant material, would deposit on these catalyst particles and organize themselves into tubular structures. It wasn't intentional. The smiths weren't trying to create nanotubes. They were just following traditional recipes, adding specific types of wood that produced good steel. But some of those woods contained trace elements that happened to catalyze nanotube formation. The smiths selected for the results better steel, without understanding the mechanism. Natural selection at the technological level. Methods that produced nanotubes, that created superior steel, were retained and passed down. Methods that didn't were abandoned or modified. Over generations, the techniques converged on processes that, unknown to their practitioners, were creating nanoscale reinforcement. The cementite nanowires formed through different mechanisms, related to how the steel cooled and was forged. During the slow cooling in the crucible, carbides began to precipitate. Under the right conditions, particular cooling rates, particular impurity concentrations, these carbides could form as elongated crystals rather than blocky particles. Nanowires instead of grains. During subsequent forging, these nanowires aligned. The mechanical working, the stretching and compressing of the steel, oriented the nanowires along particular directions. Remember those planar arrays of carbides we discussed? At the nanoscale, these arrays consisted partly of these nanowires, all aligned, all oriented to provide maximum reinforcement. The nanostructures weren't randomly distributed. They followed the impurity planes, those phosphorus-rich and sulfur-containing regions that we talked about in the previous segment. The impurities guided where the nanostructures formed, creating an organized arrangement rather than a random distribution. This organization was crucial to the steel's properties. Randomly oriented nanotubes might not provide much benefit. They might even create weak points. But aligned nanotubes, all oriented to resist the stresses that a blade experiences in use, would reinforce the steel in exactly the ways needed. When a Damascus blade was stressed, when it was bent or struck against something hard, or used to cut, the nanostructures helped distribute that stress. The nanotubes, embedded in the iron matrix, acted like reinforcing fibers. When cracks tried to form, when the metal was stressed to the point of failure, the cracks encountered these nanoscale obstacles. Crack propagation, the spreading of a fracture through a material, was deflected. A crack moving through the iron matrix would hit a carbon nanotube and stop, or be forced to go around it, dissipating energy in the process. Or it would encounter a cementite nanowire oriented across its path, and the crack would be blunted, prevented from continuing. This is how the steel achieved such remarkable toughness. This is why Damascus blades didn't shatter when they struck rock. This is why they could be flexed and would spring back. The nanoscale structure was doing what modern composite materials do. preventing catastrophic failure by interrupting crack propagation at the smallest scales. The measured tensile strength of Damascus Steel exceeded 1 gigapascal, 1 GPa. To put that in perspective, modern structural steel typically has tensile strength around 400 to 500 megapascals. Damascus Steel was more than twice as strong. It approached the strength of modern high-performance alloys, specialized steels developed with computer modeling and precise control of composition and heat treatment. And yet Damascus Steel was made in clay crucibles heated with charcoal fires, by smiths working from experience and tradition rather than from theoretical understanding. This is what makes the discovery so profound. Modern materials scientists, with all their knowledge and technology, with electron microscopes and computer simulations and precise control of manufacturing conditions, create nanocomposites because they understand the principles. They know that nanoscale reinforcement can produce exceptional properties. They deliberately engineer materials to include nanotubes or nanowires or other nanostructures. Ancient smiths created the same thing without understanding, without intending to, without even being able to see what they were making. They created nanotechnology before the concept of nanotechnology existed. They manipulated matter at the atomic scale before anyone knew that atoms existed. This challenges our assumptions about the relationship between knowledge and capability. We tend to think that you must understand something in order to create it, that theoretical knowledge must precede practical achievement. But Damascus Steel proves otherwise. You can create things far beyond your understanding if your methods are refined enough, if your observations are careful enough, if you pay attention to results rather than theory. The smiths knew that certain ores, from certain locations, produced better steel. They didn't know those ores contained the trace elements that would catalyze nanotube formation, but they knew empirically that they worked. They knew that certain woods added to the crucible produced superior results. They didn't know those woods released compounds that promoted nanoscale carbide formation, but they knew to use them. They developed quality control through observation. Good steel had certain patterns, certain appearance, certain behavior during forging. They learned to recognize these signs. The patterns we discussed earlier, those visible waves and bands, were partly manifestations of the underlying nanostructure. Master smiths learned to read them, to judge steel quality by appearance, unknowingly assessing nanoscale structure through macroscopic indicators. This is profound traditional knowledge. Not primitive, not simple, not inferior to modern scientific understanding. Different, but in its own way equally sophisticated. Based on accumulated observation across generations, refined through countless experiments, encoded in techniques and recipes, and the skilled judgment of master craftsmen. When the techniques were lost, when the chain of transmission broke, modern science took centuries to figure out what ancient smiths had known how to do. Even with electron microscopes and metallurgical theory, even with all the advantages of modern research, it was difficult to recreate. Because the traditional knowledge wasn't just about following steps. It was about judgment, about reading the material, about subtle adjustments that couldn't be captured in written recipes. The discovery of nanostructures in Damascus Steel also explained some of the legends. The blade that could shatter rock without damage, nanoscale reinforcement preventing crack propagation, the extraordinary edge retention, cement-type nanowires providing wear resistance at the cutting edge, the combination of hardness and flexibility, the composite structure balancing properties that normally conflict. The legends were true because the material science was real. The impossible feats were possible because the steel genuinely was exceptional, genuinely did things that ordinary steel couldn't match. Not magic, not exaggeration, but nanotechnology. Ancient blades, forged over 1,000 years ago, rival modern composites in their sophistication. Materials scientists today, trying to develop next-generation structural materials, are pursuing similar goals, creating nanocomposites with exceptional properties. They're using what they've learned from Damascus Steel, among other sources, to guide their work. There's a beautiful circularity here. Modern science studies ancient artifacts, discovers nanoscale structures, and uses those discoveries to inform the development of future materials. The past teaches the future. Traditional knowledge, even when not fully understood by its practitioners, contain truths that modern science can validate and build upon. And yet, we still haven't fully recreated Damascus steel. We can make steel with carbon nanotubes. That's been done. We can create composites with impressive properties. But making it through the traditional process, achieving the exact combination of nanostructures and composition and properties that historical Damascus steel had, that remains elusive. Because it's not just about having nanotubes. It's about having them in the right places, in the right orientations, in the right matrix, combined with the right carbide formations and the right impurity distributions. It's about achieving the whole package, the complete system that made Damascus steel legendary. Perhaps someday we'll completely crack the code. Perhaps modern materials science will fully understand every detail of what made Damascus steel work, and we'll be able to recreate it at will, or even surpass it. But even then, we should remember, ancient smiths got there first. Without microscopes, without theories, without formal scientific method, they created nanotechnology. They reached across 1,000 years to surprise modern scientists. They left us artifacts that still reveal new secrets when examined with cutting-edge instruments. They remind us that human ingenuity, careful observation, and accumulated traditional knowledge can achieve things that seem impossible, can create technology that seems anachronistic, can produce results that take centuries for theoretical understanding to catch up to. Rest now with this image. A Damascus blade, its surface rippling with those characteristic patterns, and within it, invisible to the naked eye, impossible to detect with medieval technology, carbon nanotubes and cementite nanowires woven through the steel matrix at scales measured in billionths of a meter. Ancient and futuristic at once. Traditional and cutting edge. A bridge between eras, between ways of knowing, between craft and science. Nanotechnology before nanotechnology. The impossible made real. The legend confirmed, at the smallest scales, where atoms themselves become architecture. There is something almost magical about accidents that create perfection. About processes where ignorance achieves what knowledge might struggle to replicate. Tonight, we explore one of history's most remarkable accidents. How ancient metallurgists, following traditions they didn't fully understand, using materials whose chemistry was invisible to them, created nanotechnology through what was essentially trial, error, and careful observation across generations. The key to understanding Damascus steel's extraordinary properties lies not in what the smiths knew, but in what they couldn't have known. In the chemistry happening inside those sealed crucibles. In the behavior of elements present in such tiny amounts that even weighing them would have been impossible with ancient instruments. In reactions occurring at temperatures and pressures that transformed simple ingredients into something extraordinary. Let us begin with the plants. Remember that the carbon source for Wood's steel wasn't pure carbon, but organic material. Wood leaves, bamboo, various plant fibers. These were placed into the crucible along with the iron. The smiths knew from experience that certain plants produced better steel than others. Perhaps the wood from a particular species of tree. Perhaps leaves gathered at a certain time of year. Traditional knowledge, passed down, refined, but never fully explained. When these plant materials were heated in the sealed crucible, they didn't simply burn away into ash. The low oxygen environment, the high temperatures, the sealed container, all of these conditions caused something different to happen. The plant materials underwent pyrolysis. Pyrolysis is the thermal decomposition of organic material in the absence of oxygen. When you burn wood in open air, it combusts. It combines with oxygen and turns to ash and smoke. But heat wood in a sealed container, where oxygen is scarce or absent, and it breaks down differently. The complex organic molecules that make up wood, cellulose, lignin, all the intricate chemistry of plant matter, begin to fall apart. The hydrogen escapes as gas. The oxygen forms compounds and escapes or combines with other elements. What remains, increasingly, is carbon. But not just amorphous carbon, not just charcoal dust. Under the right conditions, at the right temperatures, with the right catalysts present, this carbon can organize itself into structures. Carbon nanotubes, the very structures that modern scientists found embedded in Damascus steel. They weren't added deliberately. They weren't manufactured separately and mixed in. They formed right there, inside the crucible, as the plant materials pyrolyzed and their carbon atoms, freed from their original molecular structures, reorganized themselves into these extraordinarily stable tubular formations. But carbon doesn't typically form nanotubes spontaneously. It needs help. It needs the right conditions, the right temperatures, and crucially, it needs catalysts. Specific elements that promote and guide the formation of nanotubes without being consumed in the process. This is where the trace elements in the iron will become critical. Iron ore isn't pure iron oxide. Natural ores contain dozens of other elements in varying amounts. Most are present in such small quantities that they seem insignificant. Fractions of a percent, or even fractions of a fraction of a percent. Ancient metallurgists had no way to detect these traces, no way to measure them, no way to know they were there. But they were there, and some of them were exactly the elements needed to catalyze nanotube formation. Vanadium, a silvery metal, element number 23 on the periodic table. In bulk form, it's used in modern steels to increase strength and wear resistance. But in trace amounts, at the nanoscale, vanadium can act as a catalyst for carbon nanotube growth. And iron ores from certain regions, particularly some of those Indian ores used for wood steel, contain small amounts of vanadium. How small? Analysis of historical Damascus steel has found vanadium concentrations as low as 0.003%. That's 3 parts per 100,000. If you had 100,000 grains of sand, only 3 would be vanadium, an almost homeopathic concentration. Yet this was enough. At the temperatures inside the crucible, above 1,500 degrees Celsius, with carbon-containing gases swirling in the sealed atmosphere, those tiny amounts of vanadium became seed points for nanotube growth. Carbon atoms, freed from the pyrolyzing plant material, would encounter vanadium particles. The vanadium would arrange the carbon atoms, promoting their organization into the hexagonal lattice structure that forms nanotube walls. Slowly, perhaps over the hours or days of the smelting process, nanotubes would grow, extending from the catalyst particles, incorporating more carbon atoms, forming those incredibly small, incredibly strong tubular structures that would become embedded in the steel matrix as it solidified. The Smiths had no idea this was happening. They couldn't see it, couldn't measure it, couldn't even conceive of structures at the nanoscale. They only knew that ore from certain locations, processed with certain woods, produced exceptional steel. The rest was invisible chemistry. And it wasn't just vanadium. Tungsten, another element that can catalyze nanotube formation, has been found in some Damascus steel samples. Molybdenum, manganese, other transition metals in trace amounts, all potentially contributing to the formation of nanostructures. The exact cocktail of trace elements varied depending on where the ore came from, which is partly why different sources of woods had different reputations for quality. The famous steel from Golconda, from the Tamil regions, from specific mines that produced the best woods. What made them superior was probably the particular combination of trace elements in their ores. Not just iron, not just carbon, but vanadium and tungsten and other elements in just the right tiny amounts to catalyze the formations that made the steel extraordinary. This was completely unintentional. There was no deliberate engineering. No ancient metallurgist said, "We need to add 0.003% vanadium to catalyze carbon nanotube formation." They couldn't have said that. The concepts didn't exist. The knowledge was centuries in the future. Instead, they learned by results. They tried ore from different locations. They used different plants as carbon sources. They adjusted their processes. And when something produced better steel, sharper blades, tougher blades, blades with those distinctive patterns, they remembered it. They repeated it. They taught it to apprentices. They refined it over generations. Natural selection operated at the technological level. Processes that worked, that produced superior steel, survived and spread. Processes that didn't work were abandoned. Over centuries, this evolutionary approach converged on methods that, unknown to their practitioners, were creating nanoscale reinforcement through catalytic processes. The atmosphere inside the crucible played a crucial role. The sealed container created a reducing atmosphere, little free oxygen, rich in carbon monoxide and other gases from the pyrolyzing plant material. This atmosphere protected the steel from oxidation, yes, but it also created the chemical conditions favorable for nanotube formation. In open air, in an oxidizing atmosphere, any nanotubes that formed would immediately oxidize and break down. But in the sealed crucible, in that carefully controlled microenvironment created by traditional techniques refined over generations, the nanotubes could form and survive and become incorporated into the solidifying steel. Different woods, different plant materials, created slightly different atmospheres. Different combinations of gases, different trace elements released from the plant ash, different chemical environments. This is probably why certain woods were traditional for wood making, not just because they provided carbon, but because they created the right atmosphere, released the right compounds, promoted the right reactions. The smiths were manipulating chemistry without understanding chemistry. They were controlling nanoscale processes through macroscopic choices, which would to use, how long to heat, how to pack the crucible. Cause and effect separated by scales of magnitude, by invisible mechanisms, yet reliably linked through accumulated experience. And remember those impurity bands we discussed earlier? Those phosphorus-rich and sulfur-containing regions that guided pattern formation? They also controlled where and how the nanostructures aligned. As the steel solidified and was later forged, the nanotubes and nanowires didn't distribute randomly. They concentrated along those impurity bands, aligned by them, organized by them. The impurities acted like, scaffolding is perhaps the right word, templates that guided how the nanostructures arranged themselves through the steel matrix. This created organization from what could have been chaos. Random nanostructures might not provide much benefit. They might even create problems, stress concentrations, weak points. But organized nanostructures, aligned along particular planes, oriented to resist particular stresses. These provided the reinforcement that made Damascus Steel exceptional. The impurity banding, created by the crucible cooling process and by the segregation of trace elements, determined the nanostructure alignment, which determined the steel's mechanical properties, which manifested as the blade's legendary performance. A chain of causation from chemistry to physics to practical results, all invisible to the smiths, but reliably achieved through their traditional methods. But here's the fragility of it all. Change the ore, and you lose everything. If the ore didn't contain the right trace elements, if the vanadium wasn't there, or the tungsten, or whatever combination of catalysts was necessary, then nanotubes wouldn't form. You could follow the exact same process, the same heating schedule, the same types of wood, the same crucible design. But without those catalytic traces in the ore, you'd get different steel. Still functional steel, perhaps, but not Damascus steel. Not steel with nanoscale reinforcement. Not steel with legendary properties. This is probably part of why Damascus steel became impossible to recreate. The specific sources of, or that contained the right trace element combinations became depleted, or were lost, or changed in their chemistry as mines went deeper and accessed different geological layers. Or perhaps the knowledge of exactly which or sources to use was lost, part of that fragile chain of traditional knowledge that broke somewhere in the 18th century. Without the right or even perfect technique wouldn't produce Damascus steel. And without understanding what made the ore special, those trace elements measured in parts per 100,000, there was no way to know why steel from one source worked and steel from another didn't. Modern metallurgists, trying to recreate Damascus steel, had to rediscover this the hard way. They could analyze historical blades, see the nanostructures, understand the chemistry, but then they had to find or create steel with the right trace element composition. They couldn't just use any iron. They needed iron with specific impurities, in specific amounts, that would catalyze the necessary formations. This is one reason why modern Damascus steel, made through pattern welding, isn't the same. Pattern welding can create beautiful blades, can create functional blades, can even create high-performance blades. But it's not creating the nanoscale structures that defined historical Damascus steel, because it's not using the same process, not relying on those catalytic traces, not forming nanotubes through pyrolysis of plant materials in a sealed crucible atmosphere. The real Damascus steel, the historical material that became legendary, depended on a convergence of factors that was partly intentional and partly accidental. The intentional parts were the traditional techniques, refined over generations. The accidental parts were the chemistry, the nanoscale processes, the catalytic roles of trace elements that no one could see or measure or understand. Ancient smiths created a system that worked without understanding why it worked. They manipulated variables they could control, or source, plant materials, heating time, forging technique, and achieved results they desired, while remaining ignorant of the mechanisms connecting their actions to those results. This isn't unique to Damascus steel. Much traditional technology operates this way. Fermentation, for instance. Humanity made wine and bread and cheese for millennia before understanding microbiology. Traditional medicine used plants containing active compounds long before anyone could identify or synthesize those compounds. Traditional metallurgy, traditional ceramics, traditional textile dyeing, all developed through empirical observation, refined through experience, achieving sophisticated results through processes whose mechanisms remained mysterious. But Damascus steel might be the most striking example, because the gap between what was achieved and what was understood is so vast. Nanotechnology, created before anyone knew that atoms existed. Composite materials engineering, achieved before materials science was a field. Catalytic processes, employed before chemistry was formalized. The plants and the trace elements, working together in ways no one intended or understood, created something extraordinary. The plants provided carbon and created the right atmosphere. The trace elements catalyzed the organization of that carbon into nanostructures. The traditional techniques, the crucible, the sealing, the heating, the slow cooling, created the conditions where all of this could happen. Remove any one piece, and the whole system fails. Use different plants, and the atmosphere might not support nanotube formation. Use different or, lacking the catalytic traces, and nanotubes wouldn't form. Change the heating schedule, and the structures might not organize correctly. Rush the cooling, and the patterns might not emerge properly. Everything had to come together. Everything had to align. And for centuries, in certain workshops, using certain materials, following certain traditions, it did. Reliably enough that Damascus steel became famous across the known world. Consistently enough that thousands of blades were made, each one containing technology that wouldn't be deliberately recreated for over a millennium. And then the knowledge was lost. Or rather, part of the knowledge, the intentional part, the techniques, was lost. But the accidental part, the chemistry, was lost even earlier because it was never known in the first place. The smiths couldn't lose what they'd never possessed, an understanding of why their methods worked. What survived were the blades themselves. Physical evidence, waiting for science to advance far enough to examine them properly, to reveal their secrets, to show the world that ancient craftsmen had achieved something that seemed impossible, had worked with materials at scales they couldn't even imagine, had created nanotechnology through careful observation and traditional practice, through following recipes they inherited and refined, but never fully understood. The plants and the trace elements, carbon and catalysts, organic materials and metallic impurities, heat and time and sealed atmospheres, all coming together in clay crucibles, heated by charcoal fires, tended by smiths who knew what worked but not why it worked, accidentally creating perfection, unintentionally achieving sophistication, producing through traditional craft what modern science strives to replicate through deliberate engineering. This is the heart of the Damascus steel mystery. Not that it was made, we know that, we have the blades. but that it was made accidentally, through processes whose deepest mechanisms were invisible to their practitioners. That human ingenuity, careful observation, and accumulated wisdom can achieve things far beyond contemporary understanding. That you don't need to know why something works to make it work, if your methods are refined enough and your observations careful enough. Rest now with this image. A crucible, sealed and glowing hot, plant materials pyrolyzing inside, trace elements catalyzing formations at the nanoscale, while the smith outside, knowing nothing of atoms or nanotubes or catalysis, tends the fire and watches and waits, following traditions passed down through generations, creating miracles through methods he can practice but never fully explain. There is a particular kind of sadness that comes with loss, not the sudden loss of disaster or war, but the gradual fading of something precious. The slow dimming of knowledge, the quiet breaking of chains that connected generations, the imperceptible moment when the last person who truly understood something passed away without fully transmitting that understanding. This is how Damascus Steel was lost. Not dramatically, not all at once, but through a series of small failures, disconnections, and changes that accumulated over decades until one day, no one could make it anymore. Tonight, we explore this tragedy. How something so valued, so legendary, so seemingly important could simply disappear. How the knowledge that created one of history's most remarkable materials could slip through humanity's fingers and vanish for centuries. The loss wasn't sudden. There was no single moment when Damascus Steel ended. No catastrophic event, no burning of libraries, no destruction that marked a clear before and after. Instead, there was a gradual decline through the 17th and 18th centuries. Blades still being made, but becoming rarer. Quality becoming more inconsistent. The patterns becoming less distinct. And eventually, sometime around the middle of the 18th century, perhaps 1750, perhaps a bit earlier or later, the exact date is lost to history. True Damascus steel simply stopped being produced. The last smiths who could make it died. The last ingots of genuine woods were forged into blades. And then nothing. The knowledge was gone. The material was gone. All that remained were the existing blades, scattered across the world, and the legends of what they could do. But why? How could something so valuable be lost? The answer, as we'll see, lies in the very nature of what made Damascus steel work. In the dependence on specific materials, on chemistry that no one understood, on resources that seemed infinite but weren't. Let us begin with the ores. The iron ores from specific regions of India that contain those crucial trace elements, vanadium, tungsten, the catalysts that enabled nanotube formation. These ores came from particular mines, particular geological formations that had been worked for centuries. But ore deposits aren't infinite. As the centuries passed, as generation after generation of miners extracted iron from these sources, the richest veins became depleted. The ore that remained was deeper, harder to access, perhaps different in composition as the mining reached different geological layers. The vanadium-rich ores that had made the best woods, the ores from Golconda, from the Tamil regions, from the sources that had supplied smiths for over 1,000 years, these began to run out. Not all at once, not completely, but the quality changed. The concentration of trace elements shifted. What had been consistent for centuries became variable. And here's the tragedy. The smiths didn't know this mattered. They didn't know about vanadium. They couldn't measure it, couldn't test for it, couldn't know that the ore that looked identical to what they'd always used was actually critically different in its chemistry. They knew ore from certain mines produced better steel, but they didn't know why, didn't know what specific properties made the difference. So when those mines became depleted or inaccessible, when smiths had to source or from new locations, they made changes without understanding the consequences. The new ore looked right. It had the right color, the right weight, the right behavior in initial processing, but it lacked those specific trace elements in the right concentrations. And without those traces, without those catalysts, the crucible process didn't produce the same results. Nanotubes didn't form. The internal structure was different. The steel was still functional. It was still steel, after all. But it wasn't Damascus steel. It didn't have the legendary properties. The patterns didn't form correctly, or didn't form at all. Imagine being a master smith, following exactly the same techniques your father taught you, that his father taught him, going back generations. Using what seems like the same materials, heating for the same time, cooling at the same rate, forging in the same way. And the steel isn't right. The patterns don't emerge as they should. The blade doesn't perform quite as well. And you don't know why. You might try small adjustments. Different heating times, different woods, different cooling methods. Some batches might turn out better, some worse, seemingly at random. You can't see the chemistry. You can't know that the fundamental issue is the absence of 3 parts per 100,000 of vanadium in your ore. Over time, as more smiths encountered these problems, as the best ores became harder to obtain, the quality and consistency of Damascus steel declined. Some smiths might have gotten lucky, might have found ore sources that still worked, might have maintained the tradition a bit longer, but the overall trend was downward. The knowledge that depended on having the right materials became useless without those materials. And there were other disruptions, political changes, economic transformations, the gradual breakdown of the trade networks that had supplied Wootz ingots to smiths across the Middle East. The British East India Company was expanding its control over India through the 17th and 18th centuries. Eventually, large portions of India would come under direct or indirect British rule, the period known as the British Raj. And colonial administration brought changes that disrupted traditional industries. Mining taxes were imposed. Regulations changed. The British were interested in extracting resources for their own benefit, shipping raw materials back to Britain rather than supporting local industries like steel production. The economics of Wootz production shifted unfavorably. Export bans were instituted on certain goods and materials. The British wanted to protect their own steel industry, didn't want competition from Indian steel. Trade routes that had functioned for centuries were disrupted or redirected. The flow of Wootz ingots from India to the Middle East, the flow that had sustained Damascus steel production for over a millennium, was interrupted. Smiths in Damascus, in Isfahan, in other blade-making centers, found it harder to obtain quality Wootz. When they could get it, it was more expensive. Sometimes they had to make do with inferior materials. Sometimes they couldn't get Wootz at all. The entire system that had sustained Damascus steel production, the network of Indian crucible steel makers, the traders who transported ingots across vast distances, the smiths who transformed those ingots into blades, this system began to fail. Not because anyone intended to destroy it, but because economic and political changes made it unsustainable. And crucially, the knowledge of how to make Damascus steel was inseparable from access to the right materials. The techniques only worked with specific ores. The recipes were optimized for Wootz with particular properties. Without the right ingredients, the best techniques in the world wouldn't produce Damascus steel. This is different from many other traditional crafts. A potter who knows how to throw a pot can do so with different clays, adjusting technique to material. A weaver can work with different fibers. But a Damascus steel maker needed that specific Wootz, with those specific trace elements, or the whole process failed. When the materials became unavailable or changed in composition, the knowledge became useless. Recipes failed without the correct impurities. Techniques that had worked for generations suddenly didn't work anymore. And without understanding why, without knowing about vanadium and catalytic processes and nanotube formation, there was no way to adapt, no way to substitute, no way to compensate. The smiths must have been bewildered, frustrated, following traditions that had always worked, that had made their predecessors famous, and getting inferior results for no reason they could identify. Some might have blamed themselves, thinking they lacked the skill of earlier masters. Some might have thought the secrets had been deliberately hidden, that something crucial had never been taught to them. Some might have simply accepted decline as inevitable, as the way of things. But the truth was that they'd done nothing wrong. The failure wasn't in their technique, or their dedication, or their understanding of the craft, as it had been transmitted to them. The failure was in the materials, in chemistry operating at scales they couldn't perceive, in the depletion of resources they didn't know were critical. Meanwhile, in Europe, there was great interest in Damascus steel. European smiths and scholars had long admired these blades, had tried to understand their secrets. As genuine Damascus steel became rarer, as its quality declined, the mystery of how it had been made became more intriguing. But European attempts to replicate Damascus steel were based on misunderstanding. Europeans saw the patterns and assumed they were created through pattern welding, the technique they were familiar with, where different steels are forged together to create visible layers. They created pattern-welded blades and called them Damascus steel, not realizing they were creating something fundamentally different. These European imitations could be beautiful. They showed patterns, sometimes quite striking ones, but they weren't crucible steel. They didn't have the internal nanostructure. They didn't have the same properties. They were good swords, perhaps, but they weren't Damascus steel. And because Europeans thought they'd figured it out, thought pattern welding was the secret, they stopped looking for the real answer. The misunderstanding became embedded. For centuries, Damascus steel in Europe meant pattern-welded steel, creating confusion that persists even today. The true Wootz production in India collapsed sometime in the 18th century. The last crucible steel makers died without successfully training a new generation, or trained apprentices who couldn't produce the same quality because the materials had changed. The exact date is unknown. The process was gradual enough that there probably was no clear moment of ending, just a slow fading until one day, no one was making Wootz anymore. The smiths in Damascus and Isfahan, who had worked Wootz into blades, found themselves without raw materials. Some might have switched to working other steels, making different types of weapons. Some might have retired or changed professions. The workshops that had defined these cities' reputations gradually closed or shifted to other work. By the late 18th century, early 19th century, it was clear that something had been lost. There were still Damascus blades in existence, thousands of them, treasured by their owners, passed down as heirlooms. But no one could make new ones. The technique was gone, the knowledge was gone, the materials were gone, and with that loss came mystery. Because without the ability to make Damascus steel, without understanding how it had been made, the existing blades became increasingly enigmatic. How had ancient smiths created steel with such properties? What techniques had they used? What secrets had they known? The blades themselves were evidence that it was possible, proof that humans had once known how to do this. But the path from raw materials to finished blade had been lost. The chain of knowledge had broken. And once broken, it proved extraordinarily difficult to restore. Scholars began to study Damascus steel, to analyze the existing blades, to try to uncover the lost techniques. But with the metallurgical knowledge of the 18th and 19th centuries, they couldn't fully understand what they were seeing. They could observe the patterns, measure the hardness, test the blade's performance. But the nanoscale structures, the role of trace elements, the catalytic processes, all of this was invisible to them. Theories proliferated. Some thought the secret was in special heat treatments. Others thought specific forging techniques were crucial. Some believed the water used for quenching had special properties. There were legends of blades being quenched in the blood of slaves, or in water from particular rivers, or in solutions of secret ingredients. These legends probably had no basis in fact, but they filled the gap left by actual knowledge. The mystery endured through the 19th century, through the 20th century, well into the modern era. Damascus steel became a metallurgical puzzle, a challenge to scholars, a reminder that ancient peoples had achieved things that modern science struggled to understand or replicate. It wasn't until the late 20th century, until electron microscopy could reveal the nanoscale structures, until modern analytical techniques could measure trace elements in parts per 100,000, that the mystery began to unravel. And even then, even with modern knowledge and tools, recreating Damascus steel proved difficult. Because it's not just about understanding the chemistry. It's about finding or creating materials with the right composition, then processing them in ways that replicate what happened in those ancient crucibles. Modern steel production is designed for consistency, for removing impurities, for creating uniform materials. Damascus steel needed specific impurities, needed heterogeneity, needed the right contaminants in the right amounts. The loss of Damascus steel is a reminder of how fragile knowledge can be, how dependent expertise can become on specific materials and conditions, how traditional knowledge, passed down orally and through demonstration, can be lost if the chain of transmission breaks for even one generation. It's also a reminder that you can lose something without knowing what you're losing. The smiths who made the last Damascus steel probably didn't realize they were the last. They might have hoped their sons or apprentices would continue the tradition. They couldn't have known that the materials their descendants would have access to would be fundamentally different, would make their carefully transmitted techniques obsolete. And there's a poignancy in knowing that the loss was largely invisible to those experiencing it. A gradual decline in quality might be attributed to declining skill or bad luck. Difficulty obtaining materials might seem like a temporary economic problem. The breaking of trade networks might seem like just another political disruption in a world full of them. No one announced, "This is the end of Damascus Steel." There was no formal closing, no ceremony, no recognition that something precious was being lost. Just a slow fading, a gradual failure, until one day historians looking back realized that at some point in the mid-18th century, it had ended. For over 200 years, Damascus steel existed only in museums and private collections. In the blades themselves, silent witnesses to a lost art. In legends and stories that grew more exaggerated with time, until it became hard to separate truth from myth. In the frustration of metallurgists who examined these blades and couldn't quite figure out how they'd been made. The mystery endured, the legend persisted, and somewhere in laboratories and workshops around the world, people continued trying to rediscover what had been lost, to recreate what ancient smiths had achieved, to bridge the gap between past and present, between craft and science, between what was known and what was forgotten. But that search for rediscovery, that modern quest to unlock ancient secrets, that is a story for another segment. For now, rest with the image of the last true Damascus blade being forged. Somewhere, sometime in the middle of the 18th century, a smith heating an ingot, hammering it into shape, perhaps noticing that the steel isn't quite right, that the patterns aren't forming as they should, but continuing anyway, finishing the blade and never knowing that this is the last one. The last time genuine Damascus steel will be made for over 2 centuries. The end of an era, unmarked and unnoticed. The knowledge slipping away like sand through fingers, like water through cupped hands, like smoke dispersing on the wind. Gone, but not forgotten. Lost, but leaving evidence behind. Ended, but still inspiring those who would come after to search, to question, to try to reclaim what was lost. There is something deeply satisfying about mysteries being solved. About darkness giving way to light, confusion yielding to understanding. But perhaps the most satisfying mysteries are those that take not years but centuries to unravel, where generations of curious minds struggle with a problem, each adding a small piece to the puzzle, until finally, with new tools and new perspectives, the picture becomes clear. This is the story of how Damascus Steel's secrets were finally revealed, not through ancient manuscripts or recovered techniques, but through modern science looking at old objects with new eyes. Tonight, we explore the rediscovery, how 21st century technology finally explained what 8th century smiths had achieved, how electron microscopes revealed what no medieval craftsman could have seen, how the mystery that had endured for over 200 years finally began to yield its answers. The breakthrough came in 2006, not in Damascus or Isfahan, not in India where the steel had originated, but in Dresden, Germany. At the Technical University of Dresden, a team of researchers, led by Professor Peter Poffler, and including materials scientists Marian Reibold and others, decided to examine Damascus steel using the most advanced analytical tools available to modern science. They obtained samples from museum collections, sabers centuries old, that had been preserved as historical artifacts. These weren't just any blades. They were documented examples of genuine Damascus steel, with provenance establishing their age and origin. The museums allowed tiny samples to be removed for analysis. Just small pieces, carefully extracted, but enough to examine under powerful microscopes. The primary tool was transmission electron microscopy, TM, as it's called in the laboratory. This isn't the kind of microscope you might have used in school. This is technology that uses beams of electrons instead of light, that can magnify objects by millions of times, that can reveal structures at the atomic level. To use TM, you need incredibly thin samples, slices of material only a few dozen nanometers thick, thin enough that electrons can pass through them. The Dresden team carefully prepared their samples, slicing and polishing Damascus steel down to these impossibly thin sections, then placing them in the microscope. And there, revealed in the electron microscope images, were structures that shouldn't have existed in ancient steel. Carbon nanotubes, cementite nanowires, structures measured in nanometers, organized in specific patterns, embedded throughout the steel matrix. The images were startling. Clear evidence of nanotechnology in steel made over 1,000 years ago. The team published their findings in the journal Nature in 2006, and the discovery made international news. Ancient smiths had created nanostructures. Damascus steel contained carbon nanotubes. The mystery was finally being solved. But science doesn't work through single discoveries that answer everything. Science works through debate, through questioning, through the slow accumulation of evidence and the gradual refinement of understanding. And the 2006 discovery, as groundbreaking as it was, sparked as many questions as it answered. Other researchers began to examine the findings, to request access to samples, to conduct their own analyses. And not everyone agreed with all of the conclusions. John Verhoeven, an American metallurgist who had spent years studying Damascus steel, examined the evidence carefully. He didn't dispute that there were nanoscale structures. The electron microscope images were clear. But he questioned some of the interpretations. Were these really carbon nanotubes? Or were they something else? Were all the observed structures explained correctly? Verhoeven and his colleagues proposed that some of what had been identified as carbon nanotubes might actually be cementite nanowires. These are also nanoscale structures, also important to the steel's properties, but formed through different mechanisms. The distinction mattered for understanding how Damascus steel was made. This kind of scientific debate is healthy, essential even. The initial discovery had opened the door, but now the details needed to be worked out. Multiple research groups, using different analytical techniques, examining different samples, began to build a more complete picture. Transmission electron microscopy continued to be the primary tool. Samples from different blades, from different eras, from different production centers, were examined. Patterns emerged. The nanostructures weren't random artifacts or contaminants. They were consistently present in genuine Damascus steel. They varied somewhat from sample to sample, but their presence was a defining characteristic. Other techniques were brought to bear. X-ray diffraction could reveal the crystalline structure of the steel at a slightly larger scale. Energy dispersive spectroscopy could map the distribution of different elements, showing where vanadium or tungsten or other traces were concentrated. Scanning electron microscopy could show surface features and patterns. Piece by piece, image by image, analysis by analysis, the picture became clearer. The cementite nanowires were definitely there, elongated crystals of iron carbide, aligned in specific directions, providing reinforcement at the nanoscale. The carbon nanotubes were also present, though perhaps not as abundantly as initially thought. The exact proportions and distributions varied, but both types of nanostructures were real, were present, were contributing to the steel's properties. And as the structures became clear, researchers could begin to work backward, to ask, how did these structures form? What processes during the steel's production created these nanoscale features? This is where modern metallurgical theory became crucial. Scientists could use phase diagrams, charts that show how different compositions of steel behave at different temperatures, to model what happened inside the crucible. They could simulate the cooling process, the carbide precipitation, the segregation of impurities. Computer models could show how, as the molten steel cooled, carbides would begin to form. How the cooling rate would affect the size and shape of these carbides. How trace elements would segregate, concentrating in certain regions. How all of this would create the heterogeneous structure that gave Damascus steel its properties. The models matched the observations. Theory and evidence converged. Modern science could finally explain, in rigorous detail, what ancient smiths had achieved through intuition and experience. But there was another remarkable discovery waiting. One that spoke to the self-organizing properties of Damascus steel, to the way its structure wanted to exist. Researchers found that they could take Damascus steel that had lost its patterns, perhaps from over-aggressive grinding or polishing, perhaps from improper heat treatment, and restore them through thermal cycling. By heating the steel repeatedly, not even to very high temperatures, just to moderate heat and back to room temperature, repeatedly, the patterns would gradually re-emerge. The carbides would migrate. Small particles would dissolve, larger ones would grow. And this growth wasn't random. It followed the same planar arrays, the same organizational principles that had existed before. The pattern had a kind of memory, encoded in the subtle variations in composition throughout the steel. Heat it correctly, cycle it through the right temperature ranges, and the pattern would restore itself. This was Ostwald ripening in action, the same process we discussed earlier. But seeing it happen, seeing lost patterns regenerate, was profound. It suggested that Damascus steel structure was thermodynamically favorable, that it represented a low-energy state that the system naturally moved toward given the right conditions. This also explained some of the traditional techniques. Ancient smiths apparently knew that blades could be refreshed through careful heating. They might not have understood the mechanism, but they observed the results. A blade whose pattern had faded could be restored. This wasn't magic. It was chemistry and physics, the natural behavior of this particular steel composition under thermal cycling. Phase diagram modeling, using charts and equations that describe how materials transform at different temperatures and compositions, could explain the carbide precipitation. Why carbides formed as nanowires rather than as blocky particles. Why they arranged themselves in planar arrays. Why certain impurity concentrations promoted certain structures. The models showed that it was all about cooling rates, about composition gradients, about the kinetics of how atoms move through the solid steel as temperature changes. Given the right starting composition, iron with specific carbon content, and those crucial traces of vanadium and other elements, and the right thermal history, the slow cooling in the crucible, the forging cycles, the stress relief, the nanostructures would inevitably form. Ancient smiths had stumbled upon, through generations of experimentation, a process that modern materials science could now explain in detail. The traditional techniques had optimized for producing these nanostructures without knowing that's what they were doing. They just knew what worked, what produced the best steel. Science could now say why it worked. This understanding opened the possibility of recreating Damascus steel, not just making something that looked similar, but actually reproducing the material with all its properties. Several research groups and individual smiths began attempting this, using modern science to guide traditional processes. They had to source steel with the right trace elements, or deliberately add them. They had to use crucible processes, not modern steelmaking methods, because the slow cooling and the particular atmosphere in the crucible were essential. They had to forge carefully, cycling the temperature in ways that promoted nanowire alignment. Some succeeded. Modern Damascus steel, made with understanding of the underlying science, began to appear. Not in large quantities. This wasn't commercially viable, wasn't something that could be mass-produced. But as proof of concept, as demonstration that the lost art could be recovered, it was significant. The modern recreations didn't always perfectly match historical Damascus steel. The exact combination of properties, the specific patterns, the precise mechanical performance, could vary. But the essential characteristics were there. The nanostructures, the alternating hard and soft regions, the exceptional combination of hardness and toughness. And perhaps most importantly, the mystery was solved. After over 200 years of not knowing, of speculation and failed attempts and incomplete understanding, science had finally caught up to what ancient craftsmen had achieved. The journey from loss to rediscovery had taken centuries. It required the development of new technologies, electron microscopy, materials science as a formal discipline, computer modeling of metallurgical processes. It required access to historical artifacts, museums willing to allow analysis of precious objects. It required international collaboration, researchers from different countries and institutions sharing findings and debating interpretations. But in the end, understanding emerged. The ancient methods were finally understood, not just as a list of steps to follow, but in terms of what was actually happening at the atomic level. Why those steps worked, what chemistry and physics were being manipulated, how random-seeming traditional practices were actually sophisticated materials processing. This is one of the triumphs of modern science. The ability to look back, to analyze what previous generations created, and to understand it in ways they couldn't. Not to diminish their achievements. If anything, understanding the sophistication of what ancient smiths accomplished increases our respect for them. But to bring ancient craft and modern science into conversation, to bridge millennia with understanding. The Damascus Steel in museum collections isn't just historical artifacts anymore. They're case studies in materials engineering. They're examples that modern researchers can learn from. They demonstrate that traditional knowledge, developed through empirical observation and refined across generations, can achieve results that seem impossible, that can anticipate discoveries that formal science won't make for centuries. And the story isn't over. Research continues. New analytical techniques become available, offering even more detailed views of Damascus steel structure. Different samples reveal variations that teach us more about how production methods varied by region and era. Computer models become more sophisticated, better able to simulate the complex processes that created this remarkable material. Each year brings new papers, new findings, new refinements to our understanding. The mystery is solved in broad strokes, but the details continue to emerge. This is how science works, not in sudden revelations that answer everything, but in gradual accumulation of knowledge, each study adding to what came before, each researcher standing on the shoulders of those who preceded them. From ancient crucibles to modern electron microscopes, from traditional smiths to materials scientists, from mystery to understanding, the arc of discovery spanning more than a millennium, finally connecting what was lost with what has been found. Damascus Steel secrets are no longer quite so secret. The legendary properties have been explained. The impossible has been shown to be merely very difficult, very sophisticated, but possible, real, achievable through natural processes, given the right materials and the right methods. And in that understanding, there's a kind of beauty. Not the beauty of mystery, but the beauty of comprehension. The satisfaction of knowing not just that something is, but why it is. The pleasure of seeing how chemistry and physics and traditional craft all come together to produce something extraordinary. Rest now with the image of a transmission electron microscope image. Those nanotubes and nanowires revealed at last after being hidden for centuries. The invisible made visible. The unknown becoming known. Ancient achievement finally understood through modern eyes, through modern tools, through the patient work of researchers who looked at old steel and saw not just history, but science. Not just artifacts, but answers. The mystery solved. The legend explained. Damascus Steel, finally truly understood. There is a special kind of satisfaction in restoration, in taking something lost and making it live again. Not just copying its appearance, but truly understanding it, truly recreating it, bringing back not just the form, but the substance. And perhaps nowhere in materials science has this satisfaction been more profound than in the recreation of Damascus Steel. After 2 centuries of mystery, after countless failed attempts, after the slow accumulation of understanding we explored in the last segment, finally, the lost art was reborn. Tonight, we follow the story of recreation. How modern smiths and scientists, armed with understanding that their predecessors lacked, finally succeeded in making true Damascus steel again. How ancient methods were revived, refined, and in some cases surpassed using modern tools. How the legendary material was brought back from extinction. The breakthrough came in 1998. Not in a university laboratory, though universities had contributed crucial understanding. Not in a high-tech facility, though modern analytical tools had revealed the necessary secrets. The breakthrough came from the collaboration between a metallurgist and a bladesmith, John Verhoeven and Alfred Pendroy. Verhoeven was a professor at Iowa State University, a materials scientist who had spent years studying Damascus steel, analyzing historical samples, developing theories about how it had been made. Pendroy was a master bladesmith, skilled in traditional forging techniques, someone who understood steel through his hands as much as through his mind. Together, they had what neither possessed alone: scientific understanding and practical craft, theory and experience, the knowledge of what needed to happen at the atomic level, and the skill to manipulate materials to make it happen. They started with the understanding that trace elements were crucial. The historical research, the analysis of museum samples, had shown that vanadium was a key catalyst. Not much, just those few parts per 100,000, but essential. Without it, nanotubes wouldn't form. Without it, you might make good steel, but not Damascus steel. So they began with high-carbon steel and deliberately added trace amounts of vanadium. This was something ancient smiths couldn't have done intentionally. They didn't know vanadium existed, couldn't isolate it, couldn't add it deliberately. But Verhoeven and Pendroy could. They could prepare steel with exactly the composition they wanted, with precise control over even trace elements. They used crucible methods, not modern steelmaking. The slow cooling, the reducing atmosphere, the time for structures to organize. All of this was important. They couldn't shortcut the process with modern efficiency. They had to work slowly, patiently, allowing the chemistry to happen at its own pace. And they used controlled thermal cycling. This was the key insight from the modern research. Damascus steel's structure wasn't created just during initial cooling. It was refined through repeated heating and cooling cycles. Each cycle allowed the carbides to redistribute, to grow, to organize themselves more completely along their preferred planar arrays. Verhoeven and Pendroy heated their steel, then cooled it, then heated it again. Not to the extreme temperatures of forging, but to moderate heat, perhaps 700 to 800 degrees Celsius. Hot enough for atoms to migrate, for carbides to evolve, but not so hot that the structure would be disrupted. Then cooling slowly, allowing the system to relax into its preferred configuration. Cycle after cycle. 10 cycles. 20. 50. Each cycle moving the steel's internal structure closer to that thermodynamically favorable state. That organization that produced the characteristic properties. And the patterns emerged. Those distinctive waves and swirls, flowing across the steel's surface. Reliably, repeatably, not through luck or accident, but through understanding and control. The patterns appeared because the underlying structure was forming correctly. The nanostructures were aligning. The impurity bands were organizing. The steel was becoming Damascus steel. When they tested the recreated steel, it had the properties, the hardness, the toughness, the combination of characteristics that made Damascus steel legendary. It would hold an edge. It would flex without breaking. It performed as historical Damascus steel had performed. This was true recreation. Not imitation, not approximation, but the real thing, made again after 2 centuries of absence. The lost art recovered, the broken chain of knowledge restored, the mystery not just solved but reversed. Verhoeven and Pendroy published their results. They demonstrated their process. And suddenly, Damascus steel was possible again. Other smiths, other researchers, could follow their methods, could recreate the material themselves. The knowledge was no longer lost. It was documented, published, available to anyone with the skill and patience to follow it. But the story didn't end there. Because once you understand how something works, once you can recreate it, you can also improve it. You can use modern tools and techniques to refine the process, to achieve results that ancient smiths, for all their skill, couldn't have managed. Modern smiths began confirming the ancient methods, following traditional techniques, but with the understanding of why those techniques worked. They could troubleshoot failures, adjust processes, optimize results in ways that would have been impossible without scientific understanding. And they began exploring modern variations, ways to create Damascus-like steel using contemporary manufacturing methods. Not to replace traditional techniques. There's something valuable in preserving traditional craft, but to explore what might be possible with modern tools. Powder metallurgy emerged as one approach. Instead of starting with a solid ingot, start with metal powder. Steel powder, carefully prepared with the right composition, mixed with precise amounts of carbon and those crucial trace elements. The powder can be compacted under high pressure, heated to bond the particles together, creating steel with very fine-grained structure. Powder metallurgy offers control that traditional methods couldn't match. You can mix powders to achieve exact compositions. You can create structures that are impossible to achieve by melting and cooling bulk metal. You can even mix in pre-made carbon nanotubes, though getting them to align properly remains challenging. The resulting steel might not be traditional Damascus steel. The manufacturing process is entirely different, but it can achieve similar or even superior properties. Nanoscale reinforcement, exceptional hardness and toughness, the combination of characteristics that makes the material exceptional. Another modern technique is accumulative roll bonding. This involves taking layers of steel, stacking them, then rolling them together under high pressure and temperature. The layers bond, then the process repeats. Stack, roll, bond. Stack, roll, bond. Each cycle creates finer layers, more interfaces between different compositions. With enough cycles, you can create materials with layers at the nanoscale. Not quite the same as the nanostructures in traditional Damascus steel, but serving similar functions. The interfaces between layers can stop crack propagation. Different layers can have different hardness. The resulting material can have that coveted combination of hard and tough. And then there's additive manufacturing, 3D printing, but for metal. Laser-based systems that can melt metal powder layer by layer, building up three-dimensional objects with precise control over composition and structure. With additive manufacturing, you can do things that would be impossible any other way. You can vary composition gradually through the material. You can create internal structures, patterns of hard and soft regions, arranged in ways that traditional forging could never achieve. You can, in principle, design the microstructure you want, and then build it directly. Researchers have used laser additive manufacturing to replicate the microstructures found in Damascus steel. Not by following the ancient process, but by directly creating the structures that process produced. It's a completely different approach, arriving at similar results through modern technology rather than traditional craft. And remarkably, some of these modern recreations exceed historical samples in strength. Testing shows tensile strengths higher than the 1 gigapascal that historical Damascus steel achieved. Not hugely higher. We're talking about incremental improvements, not revolutionary leaps, but measurably better. This isn't surprising when you think about it. Ancient smiths were brilliant, but they were limited by their tools and materials. They couldn't measure composition precisely. They couldn't control temperature exactly. They couldn't see the structures they were creating. They achieved remarkable results despite these limitations, but they couldn't optimize in ways that modern technology allows. Modern recreations can be more consistent. Every batch can have exactly the right composition. Temperature can be controlled within degrees. Cooling rates can be programmed. The resulting steel can be analyzed at every stage, adjusted if needed, refined until it's as close to perfect as possible. This is the power of understanding combined with modern tools. You can not only recreate what ancient craftsmen achieved, you can surpass it. Not because modern people are smarter or more skilled, but because they have advantages of knowledge and technology that weren't available centuries ago. But there's a tension here, a question worth pondering. Is Damascus steel, made through powder metallurgy or additive manufacturing, really Damascus steel? It might have the same properties, the same nanostructures, the same performance. But it wasn't made the traditional way. It didn't emerge from a clay crucible, wasn't forged by hammer on anvil, doesn't carry that connection to centuries of craft tradition. There's no single answer to this question. It depends on what you value. If you care about properties and performance, about having a material with specific characteristics, then modern methods that achieve those characteristics are perfectly valid. They're Damascus steel in function, even if not in history. But if you care about tradition, about maintaining connections to historical techniques, about preserving craft knowledge that spans millennia, then there's something irreplaceable about making Damascus steel the traditional way. Following the ancient process, using methods that differ from what medieval smiths did only in the precision of modern temperature control or the purity of modern materials. Both approaches have value. The traditional methods preserve cultural heritage, maintain craft traditions, create objects with historical resonance. The modern methods enable innovation, allow improvements, make Damascus-like materials more accessible and consistent. And perhaps the most exciting possibility is that the two approaches can inform each other. Traditional smiths, understanding the science behind what they're doing, can refine their techniques in ways that weren't possible when the craft was only empirical. Modern materials scientists, respecting and studying traditional methods, can develop new processes that capture what was best about the old ways while adding new capabilities. This synthesis of old and new, of craft and science, of tradition and innovation, this might be the real legacy of Damascus steel's recreation. Not just that a lost material was recovered, but that the recovery process itself demonstrated how traditional knowledge and modern science can work together, each enriching the other. The master bladesmiths who work today, some using traditional crucible methods to make Damascus steel, aren't just recreating historical artifacts. They're keeping alive a tradition, yes, but they're also pushing it forward. They know things that ancient smiths didn't know. They can achieve consistency that would have been impossible in the past. They can teach apprentices not just what to do, but why it works, providing a more robust foundation for the craft to continue into future generations. And the materials scientists who work on Damascus steel and related materials aren't just pursuing academic curiosity. They're developing knowledge that can lead to better materials for contemporary applications. The principles learned from studying Damascus steel, how nanoscale structures can reinforce materials, how heterogeneous compositions can combine contradictory properties, how traditional processes can achieve sophisticated results. These principles apply to many modern materials challenges. Ancient steel, reborn with modern tools. Lost knowledge recovered through patient research. Traditional craft elevated by scientific understanding. This is the achievement of the recreation efforts. This is what was accomplished in the decades following Verhoeven and Pendraes' breakthrough. Damascus steel exists again, not just in museums, not just as historical curiosity, but as something that can be made, studied, refined, and used. The chain of knowledge that broke in the 18th century has been reconnected, but at a higher level than before. We not only know how to make Damascus steel again, we know why it works, what makes it special, how to optimize it. And there's something deeply satisfying about this. Something that speaks to the resilience of human knowledge, the power of curiosity and persistence. The way understanding can be lost, but then recovered, sometimes returning stronger than before. The smiths who forged the last true Damascus steel in the 18th century couldn't have imagined that, 2.5 centuries later, their craft would be resurrected. They couldn't have known that future generations would care enough to spend decades unraveling the mystery, to develop new technologies specifically to understand what they had done, to eventually succeed in doing it again. But here we are. Damascus steel lives again. The patterns flow across modern blades as they flowed across ancient ones. The nanostructures form, invisible but crucial, giving the steel its legendary properties. The legend has become reality again, not through rediscovered manuscripts or recovered secrets, but through the hard work of understanding, of careful analysis, of persistent experimentation. From loss to rediscovery, from mystery to knowledge, from legend to reality, the arc is complete. The steel is reborn. And in its rebirth, there's a lesson about the value of preserving and understanding traditional knowledge, about the power of modern science to illuminate the past, about the possibilities that emerge when craft and science work together rather than in opposition. Rest now with the image of a modern Damascus blade, just emerging from a modern smith's forge. Patterns flowing across its surface, nanostructures forming within it, properties approaching or exceeding those of the ancient exemplars. Old and new at once, past and present united. The lost art found again, ready to be carried forward into whatever future awaits. Every great story leaves echoes, ripples that spread outward through time, touching things far removed from the original event, influencing the future in ways both expected and surprising. And the story of Damascus Steel, from its creation over a millennium ago, through its loss, through its rediscovery, continues to echo today. Not just as history, not just as curiosity, but as something living, relevant, shaping how we think about materials, about craft, about the relationship between ancient wisdom and modern science. Tonight, as we reach the end of our journey through the mystery of Damascus Steel, let us explore its legacy, how this ancient material influences the modern world, what we've learned from it, and what it suggests about the future of materials science and human knowledge. Begin with the most direct legacy. Damascus Steel itself, made again, used again, valued again in the modern world. Not for swords, our era has different needs, different tools of war and peace, but for other applications where its unique combination of properties remains valuable. Luxury knives, high-end cutlery for chefs and collectors. These aren't mass-market products. Damascus Steel, whether made traditionally or through modern methods, requires too much time and skill for that. But for those who value craftsmanship, who appreciate the combination of beauty and function, Damascus Steel knives are treasured objects. The patterns alone make them distinctive. No two are quite alike, each blade carrying its own unique flow of light and dark bands. In a kitchen, in a collection, on display, they draw the eye. But they're not just decorative, they perform. They hold an edge through extended use. They're tough enough to withstand the stresses of cutting and chopping. They combine aesthetics with utility in ways that few materials can match. And beyond knives, jewelers have discovered Damascus Steel. The patterns that make blades beautiful can make jewelry striking. Rings, pendants, bracelets made from Damascus Steel, or its modern equivalents, offer something different from traditional precious metals. They're strong, more durable than gold or silver, less likely to scratch or deform. But they're also beautiful, with those organic, flowing patterns that seem almost alive. This is an interesting evolution. Damascus Steel was developed for weapons, for tools of conflict and cutting. Now it adorns fingers and necks, transformed from martial to personal, from functional to expressive. The same material, the same patterns, but repurposed for an era with different values, different needs. More surprisingly, Damascus Steel has found applications in medicine. Surgical tools, particularly specialized cutting instruments, have been made using Damascus Steel principles. The layered toughness, the resistance to catastrophic failure, the ability to maintain a keen edge, all of these properties are valuable in surgical applications. A scalpel that stays sharper longer means fewer blade changes during procedures. A surgical saw that won't shatter under stress is safer for both surgeon and patient. Tools that combine hardness at the cutting edge with toughness in the body can be thinner, lighter, more precise while remaining reliable. These aren't mass-produced, disposable tools. Medical-grade Damascus Steel instruments are specialized, expensive items. But for certain applications, for surgeries where precision and reliability are paramount, they offer advantages that justify their cost. And there are industrial applications, though perhaps not in ways you might expect. The patterns of Damascus Steel, those alternating bands of different hardness, turn out to have value beyond just the properties they provide. Modern manufacturers have learned to create similar patterns through controlled etching processes, creating blades that are more corrosion resistant, that show where patterns more clearly, that provide visual feedback about the tool's condition. Industrial cutting tools, saw blades, precision instruments. These sometimes incorporate Damascus-like patterns not because they need the exact properties of historical Damascus steel, but because the principles of combining hard and tough regions, of creating heterogeneous structures that resist failure, have proven valuable across many applications. But perhaps the most profound legacy isn't in these direct applications. It's in how Damascus steel has influenced how materials scientists think about materials design. The nanostructures found in Damascus steel, the way it combines contradictory properties, the principles it embodies, these have inspired entirely new approaches to creating advanced materials. Consider turbine blades, the components that spin at incredible speeds in jet engines and power generation turbines. These blades face extreme stresses, high temperatures, enormous centrifugal forces, corrosive environments. They need to be strong, heat-resistant, and tough enough not to fail catastrophically if damaged. Modern turbine blades often incorporate nanostructures inspired partly by Damascus steel. Not carbon nanotubes necessarily, but other nanoscale reinforcements, ceramic particles, carbide formations, deliberate patterns of different compositions at the microscopic level. The principle is the same. Use nanoscale structure to combine properties that normally conflict, to create materials that are stronger and tougher than homogeneous materials could be. Engineers designing these turbine blades study Damascus steel, not to copy it directly, but to understand the principles. How does nanoscale reinforcement prevent crack propagation? How do alternating hard and soft regions distribute stress? How can you design heterogeneity that enhances rather than undermines performance? The automotive industry has taken similar lessons. Modern high-strength steels for vehicle bodies, for crash structures, increasingly use principles similar to those that made Damascus steel exceptional. Tailored properties, harder in some regions, more ductile in others, that help vehicles absorb crash energy while protecting occupants. Stress distribution designed to prevent catastrophic failure, to manage forces in controlled ways. These modern automotive steels don't look like Damascus steel. They don't have the patterns, but they're intellectual descendants, designed using principles that Damascus steel demonstrated centuries before modern metallurgy understood why they worked. Computer modeling has become crucial to this work. Finite element simulations, complex mathematical models that predict how materials will behave under stress, can now validate what ancient Damascus steel achieved. Engineers can model a Damascus blade, simulate impacts and stresses, and see in their simulations why the blade performed as it did. These simulations confirm what testing of historical blades suggested. The stress distribution in Damascus steel was remarkably efficient. The alternating regions of different hardness, the nanoscale structures, the impurity bands, all of these features work together to spread stress throughout the blade rather than concentrating it at failure points. And having confirmed this through simulation, engineers can now design new materials that deliberately incorporate similar features. Not through traditional forging, but through modern manufacturing methods informed by understanding what made Damascus steel work. At academic conferences on materials science, on nanotechnology, on advanced manufacturing, Damascus steel appears regularly in presentations and papers. It's cited as one of the earliest examples of functional nanotechnology. Researchers present studies showing how ancient smiths, working without modern knowledge or tools, created nanoscale structures that modern scientists are still learning from. There's a certain humility in this. Modern materials science, with all its sophisticated theories and advanced instruments, looking back at ancient craft and saying, they got there first. They did something we couldn't do for centuries afterward. We're still learning from them. This challenges certain assumptions about progress. We tend to think of technological advancement as linear, as always moving forward, with the present always more advanced than the past. But Damascus Steel reminds us that this isn't always true. That knowledge can be lost. That ancient peoples could achieve things we couldn't replicate. That sometimes the past has lessons for the future. And what Damascus Steel achieved, what those ancient smiths accomplished through patient observation and accumulated experience, was mastering principles that modern science has only recently formalized. They understood empirically what we now understand theoretically. They achieved through craft what we now achieve through engineering. The principles of nanocomposite materials, of using nanoscale reinforcement to enhance bulk properties. These are cutting-edge materials science. Yet Damascus Steel embodied these principles 1,000 years ago. The ancient smiths were doing nanotechnology before we had the concept, before we could even see the structures they were creating. They were managing stress distribution in ways that finite element analysis now shows was remarkably optimal. They were creating heterogeneous materials when most metallurgy aimed for homogeneity. They were combining hard and soft, strong and tough, in materials that shouldn't have been able to combine those properties. And they did it all accidentally, or at least without conscious understanding of what they were doing at the nanoscale. They followed traditional processes, adjusted based on results, refined techniques across generations. Natural selection operating at the level of technology. Methods that worked survived, methods that didn't work were abandoned. This is perhaps the most profound lesson of Damascus Steel. You don't need to understand something at the deepest level to achieve it. Empirical observation, careful experimentation, patience, and accumulated wisdom across generations can reach destinations that formal theory hasn't yet mapped. This doesn't diminish the value of theoretical understanding. Modern science's ability to explain Damascus Steel, to understand why it worked, enabled its recreation and improvement. Theory provides power that empirical methods alone cannot match. But the story of Damascus Steel reminds us that practical wisdom, traditional knowledge, craft expertise, these have their own kind of power, can achieve their own kind of sophistication. And perhaps this suggests something about the future. As we face materials challenges that our current theories struggle with, creating materials for extreme environments, for nanoscale devices, for applications we can barely imagine, perhaps there's value in the Damascus Steel approach. Try things, observe carefully, refine based on results. Don't wait for complete understanding before attempting something. Modern materials science can combine these approaches. The empirical methods of traditional craft with the analytical power of modern theory. Experiment and measure. Try and model. Create and understand. Neither approach alone is sufficient, but together they might achieve things that either would miss. Damascus Steel proves that ancient technology can outpace modern understanding. Not forever. Eventually understanding catches up, as it did with Damascus Steel. But for centuries, for millennia potentially, practical achievement can run ahead of theoretical knowledge. This has implications for how we think about traditional knowledge generally. Indigenous metallurgy, traditional medicine, ancient agriculture. These fields contain wisdom accumulated over generations, refined through observation, optimized through long experience. Some of it might be superstition, but some of it might be sophisticated technology that we simply don't yet understand. Damascus Steel suggests we should approach traditional knowledge with respect, with curiosity, with the understanding that just because we can't explain something doesn't mean it isn't real, isn't valuable, isn't worth preserving and studying. And as we carry Damascus Steel's legacy forward, as we continue to learn from it and to apply its principles, we honor not just the material, but the people who created it. The generations of Indian metallurgists who developed wood steel. The smiths in Damascus and Isfahan who perfected blade making. The traders who connected distant civilizations. The masters who trained apprentices, preserving and refining craft knowledge. They didn't know they were creating nanotechnology. They didn't know they were solving materials science problems that would remain challenging 1,000 years later. They were just trying to make the best steel they could, following and refining traditions they'd inherited, serving the needs of their time. But what they created transcended their time. It survived the loss of the techniques that made it. It waited patiently in museum collections for science to advance enough to understand it. And now it informs cutting-edge research, influences modern materials design, reminds us of the value of both traditional craft and modern science. This is legacy. This is impact. Not just making something impressive in your own time, but creating something that speaks across centuries, that teaches future generations, that remains relevant and inspiring long after its creators are gone. Damascus Steel is more than a material. It's a bridge between eras, between ways of knowing, between craft and science. It's evidence of human ingenuity across time. It's proof that curiosity and persistence can recover what was lost. It's inspiration for what might yet be achieved. And so we end where we began, with legend. But now the legend is understood. The mystery is solved, though it continues to inspire new questions, new research, new applications. The impossible has been explained, though it remains impressive. Damascus Steel, born in ancient Indian crucibles, perfected in medieval Middle Eastern workshops, lost for 2 centuries, rediscovered through modern science, reborn through synthesis of old and new. A material that was legendary for what it could do, that became mysterious when the techniques were lost, that is now valued for what it teaches us about materials, about knowledge, about the long arc of human achievement. Its patterns still flow across blades, light and dark bands interweaving in organic complexity. But now we know those patterns aren't just beautiful. They're functional, meaningful, the visible signature of sophisticated internal structure. Now we know that within that patterned steel, invisible to the naked eye, nanotubes and nanowires reinforce the material in ways that ancient smiths created without knowing, that modern scientists can finally appreciate and emulate. The mystery of Damascus Steel isn't really a mystery anymore, but that doesn't make it any less wonderful. If anything, understanding makes it more impressive, not less. Knowing how it was made, why it worked, what made it legendary, this deepens rather than diminishes its fascination. And the story continues. New researchers studying old blades. New smiths making new steel using old principles. New applications emerging from ancient wisdom. New materials being designed based on lessons from the past. The legacy growing, spreading, touching fields and applications far from anything medieval smiths could have imagined. From ancient battlefields to modern operating rooms. From medieval trade routes to contemporary materials laboratories. From craft tradition to scientific understanding and back again. The journey of Damascus Steel continues, its story still being written, its lessons still being learned, its influence still spreading. And perhaps in another 1,000 years, people will look back at what we're doing now with materials and nanotechnology, and they'll see connections we can't yet perceive. They'll understand our achievements in ways we cannot, just as we now understand Damascus Steel in ways its creators couldn't. The conversation between past and future continues, mediated by the patient observation of the present. This is the final legacy of Damascus Steel. The reminder that human knowledge is cumulative, that each generation builds on what came before, that wisdom can be lost but also recovered, that understanding deepens with time. Ancient smiths created something extraordinary. Modern scientists explained it. Future researchers will build upon it. And the steel itself, those blades in museums, those new creations in modern workshops, remains as physical evidence, as tangible connection between all these eras. Sleep now with the image of Damascus Steel in your mind. Those flowing patterns, those invisible nanostructures, that combination of beauty and function, of tradition and innovation, of mystery and understanding. A material that spans millennia. A testament to human ingenuity across time. A legend that was real, a mystery that was solved, a tradition that was lost and found again. The mystery of Damascus Steel. Understood at last, but still inspiring wonder. Known completely, yet still teaching us. Ancient, yet eternally relevant. A bridge between what was and what will be, carrying forward lessons from the past to inform the future.